place where you are lying right now, the exact spot where your head rests against the pillow, is moving. It doesn't feel like it, of course. The room is still, the darkness is quiet, and your breathing is slow and steady. But the earth itself is turning, carrying you and your bed, and the whole building with it, spinning gently eastward, at a speed that, for most places where people live, is several hundred kilometers an hour. You don't notice it, because everything around you is moving together, and the motion is as smooth as anything in nature ever is. Right now, as you settle deeper into the mattress, that spinning is carrying you toward the night side of the planet, deeper into the quiet dark that already surrounds your room. And the Earth is not just spinning, it is also moving around the Sun, tracing a long, curving path at about 107,000 kilometers per hour. So even in this moment of complete stillness, you are traveling. Let yourself imagine that motion, not as something fast or dizzying, but as something soft and constant, like floating on a very slow, very wide river. The ceiling above you, the walls around you, the floor beneath you, all of it is part of the same drift. And if we could pull the camera back, slowly, gently, we would see the roof lift away, the neighborhood shrink, the city lights become tiny scattered sparks, and the whole curve of the Earth come into view. From up there, the planet looks peaceful, blue and white and brown, wrapped in a thin veil of air, hanging in a darkness so deep and so complete that it makes the night sky you see from the ground seem bright by comparison. That darkness is where we are going tonight, but we are not going to rush toward it. We are going to drift outward step by step, world by world, at the pace of a long, slow exhale. The solar system, the collection of worlds and smaller bodies that all travel around our sun together, began a very long time ago. About 4,600,000,000 years ago, there was no Earth, no sun as we know it, no planets at all. There was only a huge, slowly spinning cloud of gas and dust, spread out across an enormous stretch of space. This cloud was mostly hydrogen, the simplest and most common element there is, along with helium and tiny grains of heavier material. Over time, the cloud began to pull together under its own gravity, the way small things naturally drift toward larger things if they are close enough and slow enough. Most of the material gathered in the center, growing denser and hotter, until eventually it ignited into the star we call the Sun. The leftover material, the gas and dust that didn't fall into the center, flattened into a spinning disk around the young star, and from that disk, over millions of years, the planets formed. Tiny grains stuck to other tiny grains, then to pebbles, then to boulders, and so on, building the worlds we are about to visit. This is the story that the evidence points to, the best explanation we have for how the solar system came to look the way it does. But it happened so long ago, and so slowly, that no one was here to see it. We have pieced it together from clues, from the patterns we see in the orbits of the planets, and the makeup of the oldest rocks. There is much about the early solar system that we still do not know for certain, and that not knowing is part of the quiet too, part of the vastness we are about to explore. Our journey tonight will begin at the center, at the Sun, and then move outward. We will visit each planet in turn, from the smallest rocky worlds close to the star to the great gas giants farther out, and then beyond them to the icy realms at the very edge. Each world has its own character, its own quiet story, and we will take our time with each one. There is no need to hurry. The solar system is not going anywhere, and neither are you. You are exactly where you need to be, warm and still and safe, while your mind drifts out into the spaces between the worlds. The distances we will be talking about are so large that they can be hard to hold in the imagination. In our everyday lives, we measure distance in meters or kilometers, in the length of a room or the drive to work. Those numbers are small and familiar. But the distances between planets are so vast that even the numbers themselves become too big to picture. To make sense of them, we often use the speed of light as a ruler. Light is the fastest thing there is. In 1 second, a beam of light travels about 300,000 kilometers. That means it could circle the Earth more than 7 times in the time it takes you to blink. Light from the sun takes about 8 minutes to reach Earth. That is a distance of about 150 million kilometers. When you look at the sun, you are seeing it as it was 8 minutes ago. That is one way to feel the scale of even our own small corner of the solar system. And as we move outward past the outer planets, the light travel time grows. From Neptune, the most distant known planet, light takes more than 4 hours to reach us. The solar system is big enough that even light, racing along at its incredible speed, needs real time to cross it. Let that settle over you like a blanket. The distances are huge, yes, but they are also peaceful. There is so much space between the worlds that collisions almost never happen. The planets have been following their quiet paths for billions of years, and they will keep doing so long after this night is over. There is a deep, slow rhythm to the solar system, a clockwork that ticks so gently you could listen to it for a lifetime and never hear a single gear click. The Earth orbits the Sun once a year. Mars takes nearly 2 years. Jupiter takes 12. The outer worlds take decades, even centuries. And all the while, the Sun itself is moving, carrying the entire solar system with it as it orbits the center of our galaxy, a journey that takes about 230 million years to complete once. Everything is moving, but everything is moving so smoothly, so predictably, that it feels like the most natural thing in the universe. So tonight, we are going to follow that gentle motion. We are going to start at the Sun, the warm heart of the system, the source of almost all the light and heat that makes life possible on Earth. From there, we will drift outward, past the small, cratered world of Mercury, the first planet from the Sun. We will pause at Venus, the hottest world, wrapped in its thick clouds. We will look back at our own Earth and its moon, a tender pair in the vastness. Then on to Mars, the red planet, with its ancient volcanoes and dry riverbeds. We will pass through the quiet, scattered rocks of the asteroid belt, a place that is not crowded or dangerous, but mostly empty and still. Then we will enter the realm of the giants. Jupiter, the largest of all the planets, with its storms and its many moons. Saturn, with its breathtaking rings, made of countless tiny pieces of ice. Then farther still, to the ice giants, Uranus and Neptune, blue and cold and far from the sun's warmth. And finally, we will drift beyond the planets entirely, into the Kuiper Belt and the Oort Cloud, the outer reaches of the sun's influence, where the solar system fades into the darkness between the stars. This is a long journey, but you don't need to do anything. You don't need to remember the numbers or the names. You don't need to stay awake for all of it. The words will keep going, a soft stream of sound, and you can drift in and out as you please. If you miss a fact, it will come back around gently, restated in a slightly different way, so you never feel lost. The point is not to fill your head with information. The point is to let the sheer quiet scale of it all wash over you, to let the distances and the slow orbits and the patient, ancient light carry you into a deep and restful sleep. Think of the sun now, sitting at the center of everything, a steady, glowing presence. It has been burning for about 4.5 billion years, and it will keep burning for roughly 5 billion more. It doesn't hurry. It doesn't flicker with worry. It just shines, pouring its light outward in all directions, and a tiny fraction of that light falls on the Earth, and some of it falls on you, even now, even in the dark of your room, in the form of warmth stored in the air and in the walls, and in your own body. The sun is the reason there is a solar system at all. Its gravity is what holds the planets in their orbits, a gentle but firm tether that keeps each world on its path. Without the sun, the planets would simply fly off into the deep cold of interstellar space, drifting alone and dark. But the sun is there, and it is reliable, and it will rise again tomorrow, just as it has done every day for the entire history of the Earth. As you lie here, imagine that you can feel that pull, the faint, invisible thread of gravity connecting you to the sun. It is the same force that holds you to the Earth, the same force that shapes the paths of planets and moons and stars. It doesn't demand anything from you. It just holds you, quietly, like the bed beneath you, and the pillow under your head. You are part of the solar system, a tiny, living piece of it, made from the same elements that were forged in stars long before our sun was even born. The carbon in your body, the oxygen in your lungs, the iron in your blood, all of it was made in the hearts of ancient stars that lived and died billions of years ago, scattering their material across space until it eventually became part of the cloud that formed our sun and its planets. You are made of stardust, as the old saying goes, and that is not just a poetic thought. It is a literal, scientific truth. The atoms that make up your hand, resting on the blanket, once drifted through interstellar space. They were once inside a star, and now they are here, in this quiet room, breathing softly, drifting towards sleep. That is a comforting thought, and there is no need to do anything with it except let it settle. The night is long, and the journey ahead is full of quiet wonders. We will take them one by one, slowly, with long pauses and soft descriptions. There is no destination to reach, no test at the end. This is simply an invitation to float, to let your mind drift outward from the room, up through the sky, past the atmosphere, and into the silent, star-filled dark where the planets turn. The first stop on our journey is the sun, and we will begin there soon. But for now, just feel the stillness of this moment. Feel the weight of your body sinking into the bed. Feel the slow, steady rhythm of your breath. Outside, the earth is turning. The stars are shining. The solar system is following its ancient, peaceful dance. And you are part of it all, held and safe, drifting gently, gently, toward the center of it all, where the warm light of the sun is waiting. We are drifting now, slowly, toward the center of the solar system, toward the warm heart that holds everything together, the sun. It sits at the middle of everything we are about to explore, and it has been there, steady and shining, for a very long time. If you could travel toward it from where you lie right now, you would cross about 150 million kilometers of space. That is a distance so large that light itself, racing along at 300,000 kilometers every second, takes about 8 minutes to make the trip. When you step outside on a sunny day and feel the warmth on your skin, that warmth left the sun 8 minutes earlier. It traveled across the empty space between worlds, moving at the fastest speed anything can move, and it still took 8 full minutes to reach you. That gives you a sense of how far away the sun really is, and also how powerful it must be to feel so warm, even across such an enormous distance. The sun is a star. That is the simplest and most important thing to say about it. It is a star, just like the thousands of stars you can see in the night sky when you are far from city lights. The only difference is that the sun is much, much closer to us than any other star. The next nearest star, a small, dim one called Proxima Centauri, is about 4.2 light-years away. A light-year is the distance light travels in 1 year, which is about 9.5 trillion kilometers. So the sun is our star, close and familiar, while all the other stars are so far away that they look like tiny points of light, even though many of them are larger and brighter than the sun. The sun only looks so big and so bright because we are right next to it, in cosmic terms. The sun is a giant ball of gas. Not solid ground, not rock, not anything you could stand on. It is made mostly of 2 of the lightest and simplest elements there are, hydrogen and helium. About 3/4 of the sun's mass is hydrogen, most of the rest is helium, with just a tiny sprinkle of heavier elements. The sun is so enormous that it contains about 99.8% of all the mass in the entire solar system. Everything else, all the planets, all the moons, all the asteroids and comets and dust grains, everything put together makes up only about 0.2%. Jupiter, the largest planet, accounts for most of that tiny leftover fraction. The Earth is barely a speck by comparison. If you could gather up everything in the solar system except the sun and put it all on one side of a scale and put the sun on the other side, the sun would still outweigh everything else by hundreds of times. The solar system is, more than anything else, the sun, with a few small leftovers drifting around it. This giant ball of gas is held together by its own gravity. Gravity is the force that pulls things toward each other, and the more mass something has, the stronger its pull. The sun has so much mass that its gravity squeezes its own material inward with incredible force. Deep in the center of the sun, the pressure and the temperature are so high that something remarkable happens. The hydrogen atoms, squeezed together so tightly, fuse into helium. This process is called nuclear fusion, and it releases enormous amounts of energy. Every second, deep in the sun's core, about 600 million tons of hydrogen are turned into helium. And every time that happens, a little bit of mass is converted directly into energy in the form of light and heat. That energy then begins a long, slow journey outward from the core toward the surface. The core of the sun, where all this fusion happens, is staggeringly hot. The temperature there is about 15 million degrees Celsius. That number is so large it can be hard to picture. The hottest oven in your kitchen might reach 250 degrees. The surface of the sun is about 5,500 degrees, but the core is thousands of times hotter than even that. At these temperatures, matter behaves in ways that are not part of our everyday experience. The gas is so hot that it is not really a gas anymore, as we normally think of it. It is a state called plasma, where the atoms are stripped of their electrons and everything swirls together in a kind of electrically charged soup. The energy released by fusion in the core does not just shoot straight out into space. It bounces around inside the sun for a very long time. A single packet of light, a photon, can take tens of thousands of years, sometimes even hundreds of thousands of years, to travel from the core to the surface. It is absorbed by one particle, then re-emitted, then absorbed by another, over and over, in a slow, random walk through the dense interior of the star. So the sunlight that warms your face on a summer afternoon was actually generated deep inside the sun, long before modern humans ever walked the earth. It has been working its way outward since the time of the ice ages, or even longer, just to make that final 8-minute journey across space to you. The surface of the sun, the part we can see, is called the photosphere. This is the layer where the light finally breaks free and heads out into space. The photosphere is what gives the sun its bright, glowing appearance, and it is the layer whose temperature we measure at about 5,500 degrees Celsius. If you could look at the sun through a special telescope designed to protect your eyes, you would see that the photosphere is not perfectly smooth. It has a kind of grainy texture, like a pot of hot porridge gently bubbling. These grains are called granules, and they are the tops of giant columns of hot gas rising from deeper inside, cooling off at the surface, and then sinking back down. Each granule is about the size of a large country on Earth, and they last only a few minutes before being replaced by new ones. The whole surface is constantly in motion, even though from our distant perspective it looks steady and calm. Above the photosphere lies the sun's atmosphere, which has two main layers. The lower layer is called the chromosphere, a thin, reddish region that is actually hotter than the photosphere below it, reaching temperatures of tens of thousands of degrees. Why the atmosphere gets hotter as you move away from the surface, rather than cooler, is one of the questions that solar scientists are still working to understand. It seems to have something to do with the sun's magnetic field, which twists and snaps and releases energy into the upper layers, but the exact details are not yet fully settled. Above the chromosphere is the corona, the sun's outer atmosphere, which extends millions of kilometers into space. The corona is incredibly hot, reaching temperatures of 1 million degrees Celsius or more. It is so thin and diffuse that it is normally invisible, drowned out by the bright light of the photosphere. But during a total solar eclipse, when the moon passes directly in front of the sun and blocks its main light, the corona appears as a pearly, glowing halo around the dark circle of the moon. It is one of the most beautiful sights in nature, a quiet reminder that the sun is not just a simple ball of light, but a complex, layered world of its own. The sun has a magnetic field, and this field goes through a cycle that lasts about 11 years. During this cycle, the sun's magnetic activity rises and falls, like a slow, steady breathing. At the peak of the cycle, the surface is dotted with sunspots, which are darker, cooler regions where the magnetic field is particularly strong. Sunspots are only darker in comparison to the bright surface around them. If you could pull one out and look at it on its own, it would still be blindingly bright. The number of sunspots comes and goes with the cycle, and sometimes there are many, sometimes very few. This 11-year rhythm has been observed for centuries, and while we understand the basic pattern, the deep internal processes that drive the magnetic cycle are still being studied and debated. The sun is a complex place, and even with all our telescopes and probes, there are things about it that remain mysterious. This not knowing is not a problem to be solved, but simply a part of the sun's nature. It is a quiet reminder that the universe does not owe us easy answers, and that there is a certain peace in accepting that some things are still beyond our grasp. The sun is about 4.5 billion years old. It formed, as we discussed earlier, from a collapsing cloud of gas and dust, along with the rest of the solar system. In terms of the life cycle of stars, the sun is considered middle-aged. It has been shining for about 4.5 billion years, and it has enough fuel to keep shining for roughly another 5 billion years. That is a comforting thought as you lie here in the dark. The sun is not going anywhere. It will rise tomorrow, and the next day, and for billions of days after that. It is a stable, steady star, which is one reason that life on Earth has had such a long, uninterrupted stretch of time to develop and thrive. Not all stars are so steady. Some flare up and dim down unpredictably. Some are so violent that any planets around them would be sterilized by radiation. But the sun is calm and reliable, a gentle giant that has been warming our world for nearly the entire history of the planet. Eventually, of course, the sun will run out of fuel. In about 5 billion years, the hydrogen in its core will be mostly used up, and the sun will begin to change. It will swell into a red giant, expanding outward until it engulfs the orbits of Mercury and Venus, and possibly Earth. It will then shed its outer layers, creating a beautiful, glowing shell of gas called a planetary nebula, and the core will shrink down into a small, dense object called a white dwarf, which will slowly cool for billions of years more. But this is all in the very distant future, so far away that it is hard to even call it a worry. It is simply what stars do, a natural part of the life cycle that the sun is following as calmly and patiently as it has followed everything else. For now, and for a very long time to come, the sun will remain exactly as it is, a warm, steady light at the center of our solar system. The energy that the sun pours out into space is the reason there is a solar system at all, in the sense that we can see and experience. Without the sun's light, the planets would be dark, cold, invisible things, drifting through the void with no one to notice them. The sun illuminates them all. It lights up the clouds of Venus, the red plains of Mars, the swirling bands of Jupiter, the delicate rings of Saturn. Every world we are about to visit on this slow journey owes its visible beauty to the light of the sun. And the light is generous. It shines in all directions equally, not favoring any one planet over another. It is simply there, constant and reliable, the quiet heartbeat of the solar system. As you drift closer to sleep, imagine the sun sitting there in the darkness, a perfect sphere of glowing plasma, humming with its own deep internal rhythms. It does not hurry, it does not strain. It simply is. The energy that keeps it burning is the same process that powers the stars scattered all across the night sky, a process that is built into the fabric of the universe itself. And from this central star, we will now begin to drift outward, slowly, following the path of the planets. The first stop is a small, quiet world that hugs the sun more closely than any other. Its name is Mercury, and we will go there soon, carried by nothing but the slow, easy current of this narration, drifting through the silence of space toward a place of rock and shadow and extreme, quiet stillness. And so we drift outward from the sun, slowly, quietly, leaving behind the warm glow of our star and entering the deeper darkness where the planets turn. The first world we meet is a small one, Mercury. It is the closest planet to the Sun, and it is also the smallest of all the planets in the solar system. If you could place Mercury next to Earth, it would look like a tiny sibling. Mercury is only about 4,880 kilometers across, which is less than half the width of Earth. In fact, Mercury is only a little larger than our own moon. It is a world of rock and silence, a place where the sun looms huge in the sky and the ground beneath holds the scars of billions of years of impacts. As we drift closer to it now, imagine a landscape of soft gray and muted brown, rolling hills of ancient stone, and craters of every size overlapping one another like the quiet rings of raindrops on a still pond, frozen in time. Mercury orbits the Sun at an average distance of about 58 million kilometers. That is less than half the distance that Earth keeps from the Sun. From the surface of Mercury, the Sun would appear about 3 times larger in the sky than it does from Earth. It would be a vast, burning presence, dominating the daytime sky completely. And yet, despite being so close to the Sun, Mercury is not the hottest planet in the solar system. That distinction belongs to Venus, which we will visit next. Mercury is a study in extremes, a world where the temperature swings more wildly than anywhere else we know. This is because Mercury has almost no atmosphere to speak of. An atmosphere is a blanket of gases that surrounds a planet, holding in heat and softening the temperature differences between day and night. Earth has a thick, cozy atmosphere. Venus has an even thicker one, which traps heat with tremendous efficiency. Mercury has only the faintest wisp of gas around it, a thin scattering of atoms that scientists call an exosphere, and it is far too thin to hold any heat at all. Because of this, when the sun sets on Mercury, the heat of the day simply escapes into space. There is nothing to hold it in, nothing to slow its departure, and when the sun rises, the surface heats up again just as quickly. The result is a temperature range that is difficult to imagine. During the long Mercurian day, the surface can reach temperatures of over 400 degrees Celsius. That is hot enough to melt lead, hot enough to vaporize water instantly. And then, during the equally long night, the temperature plunges to nearly negative 180 degrees Celsius. That is cold enough to freeze methane, cold enough that even the most rugged materials we use on Earth would become brittle and crack. From 430 degrees above zero to 180 below, all on the same world, all within the span of a single day-night cycle. It is a quiet, patient pendulum of heat and cold, swinging back and forth in the silent void. And that day-night cycle on Mercury is very strange indeed, unlike anything we experience on Earth. On Earth, a day, the time from one sunrise to the next, is 24 hours. We are used to a steady rhythm of light and dark, one that matches the turning of our planet on its axis. Mercury turns on its axis too, but it does so very slowly. A single day on Mercury, measured from sunrise to sunrise, lasts about 176 Earth days. That is nearly 6 months of Earth time. To put it another way, you could wait from the middle of winter to the middle of summer on Earth, and in that whole stretch of time, Mercury would have experienced just one sunrise. The sun crawls across the Mercurian sky at a pace so slow that if you stood on the surface, you would not be able to detect its motion at all. It would simply hang there, a huge, blazing disk, barely moving as the hours stretched into days and the days into weeks. Stranger still, Mercury's day is actually longer than its year. A year, the time it takes a planet to complete one full orbit around the Sun, is about 88 Earth days for Mercury. So while Earth takes 365 days to circle the Sun and spins on its axis once every 24 hours, Mercury takes only 88 days to complete an orbit, but 176 days to complete a full day. The year goes by twice as fast as the day. If you lived on Mercury, you would experience this odd rhythm: 2 full orbits around the Sun, 2 full years, for each single sunrise to sunset cycle. Time would feel unmoored from the familiar patterns we know, a slow turning in the dark, a quick loop around the star, and the sun barely budging in the sky all the while. This strange relationship between the day and the year on Mercury is due to the way the planet is locked into a pattern with the sun's gravity. It is not quite tidally locked, the way our moon is to Earth, always showing the same face. But it is in a kind of 3-to-2 resonance, spinning 3 times on its axis for every 2 orbits around the sun. These rhythms are ancient and deeply settled, the result of billions of years of gravitational interaction between Mercury and the sun. There is a kind of peace in that thought, a clockwork so old and so stable that it has not changed in any meaningful way since before the first life appeared on Earth. Mercury just turns, slowly, patiently, following the path the sun's gravity has laid out for it, asking for nothing and giving nothing back but its silent, cratered surface and its slow, steady dance. That surface, as we draw closer to it now, is a landscape of profound stillness. Mercury is heavily cratered, covered in the marks of impacts from asteroids and comets that struck it over billions of years. Without an atmosphere to burn up incoming objects or weather to erode the scars, every impact is preserved almost perfectly. The surface of Mercury looks very much like the surface of our own moon, a comparison that is often made by planetary scientists. There are craters within craters, long rays of ejected material that stretch across the plains, and vast, smooth areas between the craters that are thought to be ancient lava flows, now long since cooled and solidified. The largest known crater on Mercury is called the Caloris Basin, a huge impact feature that stretches about 1,550 kilometers across. The collision that created it was so powerful that it sent shockwaves through the entire planet, creating a region of jumbled, chaotic terrain on the exact opposite side of Mercury from the impact site. It is a quiet reminder of the violence that was common in the early solar system, a violence that has now mostly settled into the calm, orderly orbits we see today. There is water ice on Mercury, which may seem impossible for a world where the daytime temperatures are hot enough to melt lead. But the ice exists in places that never see the sun. Near the poles of Mercury, there are craters whose floors are in permanent shadow. Because Mercury's axis is tilted very little, almost perfectly upright, the sun never climbs high enough to shine into these deep, dark basins. In those shadows, the temperature stays cold enough to preserve water ice, possibly delivered by comets over billions of years. This has been confirmed by spacecraft that have orbited Mercury and bounced radar signals off the ice at the poles. So even on the planet closest to the sun, there are places of permanent night, pockets of cold and darkness where ancient ice rests, undisturbed, waiting out the eons. Mercury also has a secret hidden deep inside. Despite being so small, Mercury has a very large iron core. In fact, the core takes up about 85% of the planet's radius, a much larger fraction than Earth's core occupies. This iron core generates a magnetic field, though it is much weaker than Earth's, only about 1% as strong. The existence of this magnetic field was a surprise when it was first detected, because small planets are not supposed to have molten cores capable of generating such a field. The exact reasons for Mercury's large core and its lingering magnetic field are still being investigated, and there is much that is not yet settled. It may be that Mercury was once a larger planet, and its outer layers were stripped away by a giant impact or by the intense heat of the young sun. But this is an idea, not a certainty, and the not knowing is part of the quiet mystery of this small world. As we drift past Mercury now, we can see it hanging there in the darkness, a tiny crescent of gray rock lit by the sun from one side, the rest of it lost in shadow. It is a world of extremes and silences, a place where the sun barely moves, where the ground bakes and freezes in a slow, patient rhythm, and where the only sound is the complete absence of sound. No wind, no rustling, no murmur of life. Just rock and metal and a thin scattering of atoms, bound loosely by gravity and bathed in the fierce, steady light of the nearby star. Mercury is the first waypoint on our journey outward, and it is a quiet one. a place to pause and appreciate the sheer range of conditions that exist within our own solar system. From here, we will continue our slow drift away from the Sun. The next world we will encounter is very different from Mercury, despite being relatively close in distance. It is a planet wrapped in thick, pale clouds, a world that shines brightly in our evening and morning skies. It is often called Earth's twin, because it is nearly the same size, but the similarities end there. Venus waits for us now, a world of heat and pressure and slow backward motion, and we will drift toward it gently, carried on the same quiet current that has brought us this far. For now, let Mercury recede slowly behind us, a small, quiet world that has orbited its star in silence for billions of years, and let the peace of that long, patient turning settle deeper into the quiet of your own room. Venus waits for us now, a world of heat and pressure and slow, backward motion, and we drift toward it gently, carried on the same quiet current that has brought us this far. Mercury recedes behind us, that small, battered ball of rock still turning in its patient, silent rhythm around the Sun. Ahead of us, Venus glows. If you have ever looked up at the evening sky just after sunset, or the morning sky just before sunrise, and seen a bright, steady point of light that outshines everything except the moon, you have likely seen Venus. It is often called the evening star or the morning star, though it is not a star at all. It is a planet, our nearest planetary neighbor, and it shines so brightly because its thick clouds reflect most of the sunlight that falls on them. That soft, beautiful glow from Earth is our first hint that Venus is a world wrapped in a deep, dense blanket of air. Venus is often described as Earth's twin, and there is a reason for that. It is almost the same size as Earth. The diameter of Venus is about 12,100 kilometers, only slightly less than Earth's 12,742 kilometers. The mass of Venus is about 82% of Earth's mass. If you could place the two planets side by side in space, they would look like siblings, nearly identical in size and in the way their gravity would pull on you if you stood on their surfaces. But the similarities end very quickly once you look beneath the clouds. Venus and Earth are twins only in size. In almost every other way, they could hardly be more different. The most striking difference is the atmosphere. Venus has an atmosphere that is astonishingly thick and heavy. On Earth, the air we breathe is mostly nitrogen and oxygen, with just a trace of other gases. The pressure of that air at sea level is what we are used to, what our bodies are built for. On Venus, the atmosphere is made almost entirely of carbon dioxide, a gas that traps heat very effectively, and there is so much of it. The atmospheric pressure at the surface of Venus is about 90 times what it is on Earth. To feel that same pressure on Earth, you would have to dive about 900 meters under the ocean. Standing on the surface of Venus would feel like having a kilometer of water pressing down on you from all sides. The air there is not just thick, it is crushing. Any spacecraft that has managed to land on Venus has survived for only a short time, sometimes just minutes, before the pressure and the heat destroy its instruments. And the heat. Venus is the hottest planet in the solar system, even though it is not the closest to the Sun. Mercury, as we saw, gets very hot during its long day, but it also gets very cold at night. Venus never cools off. Its average surface temperature is about 464 degrees Celsius, and that temperature is nearly the same everywhere on the planet, day and night, equator to pole. It is hot enough to melt lead, hot enough that zinc and tin would flow as liquids across the ground. The reason for this relentless, uniform heat is the carbon dioxide atmosphere. Sunlight can pass through the clouds and reach the surface, where it warms the rocks. But when that heat tries to radiate back out into space, the carbon dioxide traps it, holding it close like a thick blanket that cannot be pulled off. This is the same greenhouse effect that warms our own Earth to a comfortable level, but on Venus it has run away to an extreme degree. The planet is locked in a state of permanent, suffocating heat. The clouds that make Venus so beautiful from Earth are not made of water vapor, like the clouds we know. They are made mostly of sulfuric acid. High in the atmosphere, sulfur dioxide and water vapor react to form droplets of acid that float in thick layers, obscuring the surface completely. From above, Venus looks smooth and featureless, a pale, yellowish-white ball with almost no visible detail. But beneath those clouds, the surface is a landscape of strange and ancient geology. We know what the surface looks like because spacecraft have used radar to peer through the clouds, bouncing radio waves off the ground and building up detailed maps. What those maps reveal is a world shaped by volcanism on a massive scale. Most of the surface of Venus is covered in smooth, solidified lava plains. There are thousands of volcanoes, some of them enormous, and strange features that look like pancake-shaped domes and long, winding channels where lava once flowed. Whether any of these volcanoes are still active today is something that is not yet known for certain. The evidence hints that Venus may still be geologically alive, but the thick clouds make it difficult to study directly. Another peculiar thing about Venus is the way it spins. Most planets rotate on their axes in the same direction that they orbit the Sun. If you looked down on the solar system from above, you would see most planets spinning counterclockwise, like a dancer turning in the same direction she circles the floor. Venus does the opposite. It spins clockwise, very, very slowly. Its rotation is said to be retrograde, which simply means backward. If you stood on the surface of Venus and could somehow see through the clouds, you would watch the sun rise in the west and set in the east, the reverse of what we see on Earth. And you would have to be very patient to see it happen, because a day on Venus is incredibly long. Venus takes about 243 Earth days to complete one full rotation on its axis. That is longer than its year, which is about 225 Earth days. So on Venus, a day truly is longer than a year. The sun would crawl across the sky at a pace so slow it would be almost imperceptible, taking months to go from horizon to horizon. Why does Venus spin backward and so slowly? This is one of the questions that the science is still working on. The leading idea is that Venus may have been struck by a very large object early in its history, an impact so powerful that it flipped or slowed the planet's rotation. But this is not certain. The early solar system was a chaotic place, with many large bodies moving in unstable orbits, and Venus, like all the planets, carries the marks of that chaotic youth in ways that are not always easy to read. What we do know is that the slow, backward spin is just one more way that Venus is a world of deep, quiet strangeness. There is no moon around Venus. It is one of only 2 planets in the solar system with no moon at all, the other being Mercury. Why Venus lacks a moon is not fully understood. Perhaps it never captured one. Perhaps it once had a moon that was lost or destroyed. We simply do not know. The night sky of Venus, if you could see it through the clouds, would be moonless, a vast blackness above the glowing acid haze, with no companion to mark the passage of time. As we drift past Venus now, we can picture it hanging there in space, a world the size of Earth but utterly different in character. The surface is hidden, a secret kept beneath layers of bright, reflective cloud. The air is heavy and hot and poisonous to life as we know it. The ground is a baked volcanic plain, crossed by ancient lava flows and dotted with mountains that have never felt a drop of rain. And yet, for all its harshness, Venus is a place of a certain kind of peace. There is no weather in the sense we know it, no storms except perhaps the slow, silent turning of the upper clouds. The surface is still, the rocks unchanging, the heat constant and unvarying. It is a world that has settled into a stable, extreme state, and it will remain that way for eons to come. Venus has been a subject of human curiosity for a very long time. Ancient civilizations watched it in the sky, named it for goddesses of love and beauty, and wove it into their stories and calendars. Even in the modern era, before we knew the true conditions on its surface, writers imagined Venus as a lush, tropical world, perhaps covered in oceans and jungles. The reality turned out to be quite different, and there is a gentle lesson in that. The universe does not arrange itself for our convenience or our expectations. It is what it is, and there is a quiet beauty in discovering it as it truly exists, rather than as we might wish it to be. From Venus, we continue our slow drift outward. The next world we will encounter is one we know intimately, the one place in the universe where we are certain that life exists. It is a pale blue dot, a world of water and cloud and green growing things, and it is waiting for us just a little farther from the sun. We will pause there for a while, long enough to appreciate its quiet, familiar beauty, and to look at its constant companion, the moon. For now, let Venus recede behind us, a bright pearl wrapped in its acid clouds, turning slowly backward in the warm, thick silence of its own atmosphere, a world of heat and mystery and deep, abiding stillness. Venus recedes behind us now, that bright pearl wrapped in its acid clouds, turning slowly backward in the warm, thick silence of its own atmosphere, a world of heat and mystery and deep, abiding stillness. As we drift farther from the sun, we come to a world that is, for us, more than just a point of light in the sky. It is home. It is the place where you are lying right now, the place where every human being who has ever lived was born and died, the one world in the entire universe that we know for certain holds life. From out here, seen from a distance, Earth is a small, blue and white sphere, hanging in the darkness like a marble of astonishing beauty. The blue comes from the oceans, which cover about 70% of the surface. The white comes from the clouds, great swirls and bands of water vapor that drift through the atmosphere. And here and there, you can see the brown and green of the continents, the shapes that mapmakers have drawn for centuries, now visible as they truly are, islands of rock and soil in a vast global sea. Earth is the third planet from the Sun, sitting at a distance of about 150 million kilometers. That distance turns out to be a very fortunate one. It places Earth in what some people call the habitable zone, or the Goldilocks zone, the region around a star where temperatures are not too hot and not too cold for liquid water to exist on the surface. Water is the key. Every living thing we know of, from the smallest bacteria to the largest whale, needs liquid water to survive. Earth has it in abundance. The oceans are deep and wide, and they cover most of the globe. Even in the driest deserts, water exists as vapor in the air, or deep underground waiting to be found. This water is not just sitting still. It moves. It evaporates from the ocean surface, rises into the sky, forms clouds, falls as rain or snow, runs in rivers back to the sea, and begins the cycle again. This endless, gentle circulation of water is one of the things that makes Earth so alive, so different from the worlds we have visited so far and the ones we will visit next. The atmosphere of Earth is another gift. It is made mostly of nitrogen, about 78%, and oxygen, about 21%, with small amounts of other gases like argon and carbon dioxide. That oxygen is almost entirely the product of life itself. Billions of years ago, tiny organisms in the oceans began to release oxygen as a waste product of their metabolism, and over vast stretches of time, that oxygen built up in the air until it reached the levels we breathe today. The atmosphere does more than just provide air to breathe. It also shields the surface from the worst of the sun's radiation. High above the ground, a layer of ozone, a special form of oxygen, absorbs much of the ultraviolet light that would otherwise damage living cells. And the atmosphere burns up most of the small rocks and dust grains that enter it from space, turning them into harmless streaks of light we call shooting stars, before they ever reach the ground. Earth has another shield, one that is invisible, but just as important. Deep inside the planet, the movement of molten iron in the core generates a magnetic field. This field extends far out into space, forming a protective bubble around the entire planet. The solar wind, a stream of charged particles that flows constantly outward from the sun, is deflected by this magnetic field. Instead of striking the atmosphere directly and stripping it away, as may have happened on Mars long ago, the solar wind slides around the magnetic bubble and continues on its way. Without this magnetic shield, Earth might have lost much of its air and water over the eons, and the surface might have become a much harsher place. But the field is there, generated by the slow churn of liquid metal thousands of kilometers beneath your feet, and it has been there for most of Earth's history, a quiet, invisible guardian. And then there is the moon. As we pause here at Earth, we turn to look at its constant companion, the moon that has circled our planet for almost as long as the planet has existed. The moon is about 384,000 kilometers away from Earth on average. That is close enough that it looms large in our night sky, a familiar, comforting presence that changes its shape in a slow, predictable cycle, from a thin crescent to a full, glowing disk and back again. The moon is about 1/4 the diameter of Earth, making it unusually large relative to its parent planet. Most moons in the solar system are much smaller compared to the worlds they orbit. Our moon is an exception, and its size has important effects. Its gravity pulls on Earth's oceans, creating the tides, a slow, rhythmic rise and fall of the sea that has shaped coastlines and influenced the evolution of life for billions of years. The moon is thought to have formed in a dramatic event very early in Earth's history, about 4.5 billion years ago. The leading explanation, which is supported by a good deal of evidence but is still studied and debated in its details, goes like this. Not long after Earth itself had formed, it was struck by another large body, perhaps the size of Mars. This object has been given the name Theia. The collision was not a glancing blow, but a massive, world-shaking impact that vaporized much of the young Earth and the impactor alike. The debris from this collision was thrown into orbit around Earth, a ring of molten rock and dust. Over time, perhaps in as little as a few years, or as long as a few thousand years, that debris came together under its own gravity to form the moon. This is the giant impact hypothesis, and it explains many of the features we see. The moon's rocks are very similar to Earth's mantle rocks, but they are missing the lighter elements that would have been boiled away in the heat of the collision. The moon also has a very small iron core, consistent with the idea that the impactor's iron core merged with Earth's, while the moon formed mostly from the lighter, rocky material of the mantles of both bodies. This is the story that fits the evidence best, but it is important to say that it is not a certainty. No one was there to witness it. The collision happened so long ago that the traces are faint and fragmentary. There are other ideas, other variations on the theme, and scientists continue to examine the rocks brought back from the moon by the Apollo missions, looking for clues. The moon, for all its familiarity, still holds mysteries. How exactly did it form? How much of its material came from Earth and how much from Theia? These questions remain open in their finer points, and that not knowing is part of the quiet poetry of the moon, hanging up there in the night sky, familiar and strange all at once. The moon is slowly moving away from Earth. Every year, it drifts about 3.5 centimeters farther out. This is a very small amount, barely the width of your thumb each year, but over millions and billions of years it adds up. The reason for this slow retreat has to do with the tides. Earth's rotation is gradually slowing down due to the gravitational interaction with the moon, and as Earth slows, the moon moves outward, obeying the quiet laws of physics that govern all moving things. This is not something to be concerned about. It is a process so slow that it will take billions of years to make a significant difference, and by the time the moon is noticeably farther away, the sun will be nearing the end of its life anyway. For now, the moon is right where it has always been, as far as human memory and history are concerned, a steady, unchanging light in the darkness. The surface of the moon is a place of absolute silence and stillness. It has no atmosphere to speak of, only a very faint exosphere of scattered atoms, much like Mercury. There is no wind, no weather, no erosion, except what is caused by the slow rain of micrometeorites and the extreme temperature changes between day and night. The surface is covered in a fine, gray dust called regolith, the product of billions of years of impacts grinding the rocks into powder. The footprints left by the Apollo astronauts more than half a century ago are still there, perfectly preserved, and they will remain there for millions of years unless a meteorite happens to strike exactly in that spot. The moon has dark, flat plains called Maria, which are ancient lava flows, and bright, heavily cratered highlands that are even older. The far side of the moon, the side that faces away from Earth, is more heavily cratered than the near side, and the reason for this asymmetry is another of those lunar mysteries that is not yet fully explained. From the moon, the Earth would appear about 4 times larger than the moon appears from Earth. It would hang in the black sky, a blue and white marble, slowly turning, and it would never rise or set because the moon is tidally locked, always showing the same face to its planet. The Earth would go through phases, just as the moon does, from a thin crescent Earth to a full, glowing Earth and back again. It would be a beautiful sight, a quiet reminder of home for any traveler who might one day stand on that dusty surface and look back. As we pause here in space, looking at this familiar world and its companion moon, there is a deep sense of tenderness. This is the place where every story you have ever heard took place. Every lullaby, every whispered goodnight, every soft breath of a sleeping child, all of it happened right here, on this small, blue world. The Earth is fragile only in the sense that its living skin is thin, a delicate layer of air and water, and life clinging to a ball of rock. But the planet itself is sturdy, and it has endured for more than 4 billion years. It will endure for billions more, long after we are gone, long after the moon has drifted a little farther away and the continents have rearranged themselves into new shapes. There is a peace in that, a deep, abiding peace in knowing that the world does not depend on us to keep turning. It has its own rhythms, its own slow dances, and it will continue them, quietly, steadily, whether we are here to watch or not. From here, we will continue our slow drift outward, away from the warmth and familiarity of Earth, away from the quiet, cratered face of the moon. The next world we will meet is smaller and colder than our own, a planet of rusty red deserts and ancient, towering volcanoes. It is Mars, and it waits for us in the darkness beyond Earth's orbit. A world that may once have had rivers and lakes, a world that still holds secrets about the possibility of life beyond our own small sphere. We will drift toward it now, slowly, gently, leaving home behind but carrying its warmth with us as we go. We drift outward now, leaving behind the blue and white comfort of Earth, leaving behind the quiet, cratered face of the moon, and we move into the darker, colder reaches beyond. The next world that awaits us is Mars. It is the 4th planet from the Sun, and it orbits at an average distance of about 228 million kilometers, which is about half again as far from the Sun as Earth is. From this distance, the Sun appears smaller and dimmer in the Martian sky, a pale disk rather than the blazing presence we know. Mars is a smaller world than Earth, with a diameter of about 6,780 kilometers, just over half of Earth's size. Its gravity is weaker too, only about 38% of what we feel on our own planet. If you stood on Mars, you would weigh less than half of what you weigh here, and each step you took would feel light and easy, as if you were walking through a dream. Mars is known as the Red Planet, and the reason for that is simple and a little bit beautiful. The soil and rocks on the surface of Mars are rich in iron oxide, which is the same chemical compound that we commonly call rust. When iron is exposed to oxygen and moisture, it takes on that familiar reddish-brown color, and on Mars, the surface is coated in a fine layer of this rusty dust. The dust is so light that it gets picked up by the thin winds and carried across the planet, staining the sky a pale butterscotch or salmon pink during the day, and tinting the sunsets a cool blue. The whole world has a warm, muted glow to it, like a desert seen through a soft, dusty filter. It is a quiet landscape, ancient and still, but it has features that are anything but small. Mars is home to some of the most dramatic geography in the entire solar system. The tallest volcano we know of anywhere rises on Mars. It is called Olympus Mons, and it is a shield volcano, which means it was built up over millions of years by very runny lava that spread out in thin, wide layers before cooling. Olympus Mons is enormous. It stands about 22 kilometers high, which is more than twice the height of Mount Everest, the tallest mountain on Earth. But height is only part of the story. The base of Olympus Mons is about 600 kilometers across, roughly the distance from New York to Pittsburgh or from London to Edinburgh. If you stood on the summit and looked out, you would not be able to see the base because it would be hidden beyond the horizon, the gentle slope of the volcano curving away into the distance. The entire mountain is so large that it creates its own weather patterns, and its peak pokes up above most of the thin Martian atmosphere. It has likely been quiet for millions of years, a silent giant standing guard over an ancient landscape. Not far from Olympus Mons is another wonder, a canyon system called Valles Marineris. This is not just a canyon in the way we think of the Grand Canyon on Earth. Valles Marineris stretches for thousands of kilometers, more than 4,000 kilometers from end to end, which is roughly the width of the entire United States. In places, it is up to 7 kilometers deep, which is more than 4 times the depth of the Grand Canyon. The walls of the canyon are steep and layered, showing the geological history of the planet like the pages of a book. How exactly Valles Marineris formed is not fully settled. It is not a river canyon carved by flowing water. It is thought to be a giant crack in the crust of the planet, a rift valley formed by tectonic forces as the planet cooled and shifted early in its history. But the details remain subjects of study and quiet debate. What is clear is that Valles Marineris is a scar of immense scale, a quiet reminder that Mars, though small and cold, was once a geologically active world. And then there is the water. This is the great mystery of Mars, the question that keeps drawing our attention back to this small red world. Today, the surface of Mars is dry. There is no rain, no rivers, no lakes or seas, but there is strong evidence that this was not always the case. Orbiting spacecraft have sent back images of features that look very much like dry riverbeds, ancient deltas, and lake basins. Rovers on the ground have found minerals that only form in the presence of liquid water. The surface is marked with the ghosts of water, traces of a wetter, warmer past that may have lasted for hundreds of millions of years. Where did the water go? Some of it likely escaped into space, the victim of Mars's weak gravity and the slow stripping action of the solar wind, which, unlike on Earth, was not deflected by a strong magnetic field. Some of it is still there, frozen beneath the surface as ice, or locked in the polar ice caps, which grow and shrink with the Martian seasons. The north and south poles of Mars are covered in layered deposits of water ice and carbon dioxide ice, and these caps are permanent features, though their size changes slightly over the course of the Martian year. If Mars once had liquid water on its surface for long periods, then it is natural to wonder whether it might have also had life. Water is the one thing that all life on Earth requires, and if it was present on Mars in abundance, then the conditions for life as we understand it may have existed there too. But whether life ever actually arose on Mars remains unknown and unresolved. No direct evidence of past or present Martian life has been found. The rovers and landers that have explored the surface have looked for signs, chemical traces, microscopic fossils, but so far the results have been inconclusive. There are hints and intriguing signals, but nothing that can be called proof. The search continues, slowly and patiently, and for now the question of life on Mars is an open one, a quiet mystery that adds to the planet's gentle, melancholy beauty. Mars has 2 moons, but they are very different from our own moon. They are small, irregularly shaped objects named Phobos and Deimos, which mean fear and terror in Greek mythology, the sons of the war god Ares, whom the Romans called Mars. But the moons themselves are not fearsome at all. They are small, dark, and lumpy, more like captured asteroids than the round, stately moon we are used to. Phobos is the larger of the 2, but it is still only about 22 kilometers across at its widest point. Deimos is even smaller, about 12 kilometers across. Both moons are thought to be captured asteroids, pulled into orbit around Mars by its gravity long ago. They are covered in craters and dust, and they orbit relatively close to the planet. Phobos is so close that it actually orbits Mars faster than Mars itself rotates, which means that from the surface of the planet, Phobos would rise in the west and set in the east, opposite to the way our moon behaves. And Phobos is slowly spiraling inward. In tens of millions of years, it will either break apart into a ring of debris or crash into the surface of Mars. It is a slow, patient process, barely perceptible on any human timescale, and it adds a quiet note of impermanence to the Martian system. The atmosphere of Mars is very thin, only about 1% as thick as Earth's atmosphere at sea level. It is made mostly of carbon dioxide, with small amounts of nitrogen and argon. Because the air is so thin, it cannot hold much heat. The average temperature on Mars is about -60 degrees Celsius. It can get as warm as 20 degrees Celsius near the equator on a summer day, but even then the air is so thin that the warmth would not feel the same as it does on Earth. And at night, even in summer, the temperature can drop by 100 degrees or more, plunging far below freezing. The thin air also means that the sky is not blue, but a dusty pinkish tan during the day, and that any liquid water on the surface would either freeze or boil away almost instantly, because the pressure is too low for liquid water to be stable. Dust storms are a common feature on Mars. Because the atmosphere is thin, the winds are not strong in the way we experience wind on Earth, but they can still lift enormous amounts of fine dust into the air. Sometimes, these storms grow until they cover the entire planet, a global veil of dust that hides the surface from view for weeks or months. These planet-wide dust storms are a regular occurrence, happening every few years, and they transform Mars into a featureless, hazy ball. Then, slowly, the dust settles, the air clears, and the familiar dark markings and bright polar caps reappear. It is a slow, quiet cycle, a kind of breathing, inhaling dust and exhaling clarity. Mars has been visited by many spacecraft over the decades, more than any other planet besides Earth. Orbiters circle it, mapping its surface and studying its atmosphere. Landers and rovers have touched down on its plains and crawled across its rocks, drilling, analyzing, photographing. The names of these missions have become part of the planet's story: Viking, Pathfinder, Spirit, Opportunity, Curiosity, Perseverance. Each has added to our understanding, and each has raised new questions. The more we learn about Mars, the more we realize how much there is that we do not yet know, and that not knowing is not a frustration. It is an invitation to keep looking, to keep drifting in thought toward that small red world and wondering what it might have been like, long ago, when the rivers ran and the lakes were full. As we leave Mars behind and continue our slow drift outward, we are moving toward a different kind of place altogether. The inner solar system, with its rocky worlds and solid surfaces, is behind us now. Ahead lies a region of scattered remnants, a place where the material of the early solar system never quite came together into a planet. It is the asteroid belt, and it stretches between Mars and the next planet, Jupiter, a wide, quiet region filled with millions of rocky objects of all sizes. We will drift through it slowly, taking in its stillness and its scattered, patient light. The red glow of Mars recedes gently behind us, a world of ancient volcanoes and dry riverbeds, a world of dust and quiet questions, and we move on, out into the deepening dark. The red glow of Mars recedes gently behind us now, a world of ancient volcanoes and dry riverbeds, a world of dust and quiet questions, and we move on, out into the deepening dark. Ahead of us lies a region that is not a planet, not a single world, but a vast, scattered collection of rocky objects. This is the asteroid belt. It is a quiet interlude between the inner planets we have already visited, small and rocky and close to the sun, and the outer planets that are still to come, enormous worlds of gas and ice that dominate the far reaches of the solar system. The asteroid belt sits in the space between Mars and Jupiter, and it is a place of stillness and slow motion, a place where millions of small bodies follow their own patient orbits, each one a tiny world unto itself. The asteroid belt is often imagined as a crowded, dangerous region, a kind of cosmic obstacle course where rocks tumble and collide, and spacecraft must swerve to avoid them. This image comes mostly from movies and stories, and it is not accurate. The truth is much quieter, much more peaceful. The objects in the asteroid belt are spread out across an enormous volume of space. The belt itself is shaped like a huge, flattened ring, stretching from about 2.1 astronomical units to about 3.3 astronomical units from the Sun. An astronomical unit is the average distance from the Earth to the Sun, about 150 million kilometers. So the belt is a wide band, hundreds of millions of kilometers across, and within that band, the individual asteroids are separated by vast distances. On average, if you were standing on one asteroid, the next sizable asteroid would be hundreds of thousands of kilometers away, far enough that you could not see it with the naked eye. It would be a distant point of light, if it were visible at all. The belt is mostly empty space, a calm, silent expanse, dotted here and there with small, rocky bodies. Spacecraft have passed through the asteroid belt multiple times, and they have done so without incident. The Pioneer and Voyager probes went through it on their way to the outer planets. The Galileo spacecraft went through it on its way to Jupiter. The Cassini spacecraft went through it on its way to Saturn. None of them encountered any danger because the odds of hitting an asteroid, even by accident, are extremely small. The navigators who plan these missions do not even bother to plot a course around the asteroids. They simply fly through the belt, trusting to the enormous distances between objects to provide a clear path. And they are always proven right. The asteroid belt is a place of gentle scattering, not a place of chaos. The belt is thought to be leftover material from the formation of the solar system about 4.5 billion years ago. When the planets were forming from the disk of gas and dust around the young sun, most of the material in this region never came together to form a single planet. The reason for this is largely the influence of Jupiter, the giant planet that orbits just beyond the belt. Jupiter's gravity is enormous, and it stirred up the material in this region, preventing it from clumping together into a planet-sized body. Instead of one large world, the material remained as millions of smaller ones, ranging from tiny dust grains up to objects hundreds of kilometers across. The total mass of everything in the asteroid belt is quite small, only about 4% of the mass of our Moon, and about a third of that mass is contained in just one object, Ceres. So the belt is not a failed planet so much as a region that was never allowed to become one, kept scattered and quiet by the gentle but insistent pull of Jupiter's gravity. Ceres is the largest object in the asteroid belt, and it is a special case. It is large enough, about 940 kilometers in diameter, that its own gravity has pulled it into a round shape. This is one of the defining features of a dwarf planet, a category of objects that are round like planets, but have not cleared their orbits of other debris. Ceres is classified as a dwarf planet, and it is the only dwarf planet in the inner solar system. Its surface is dark and heavily cratered, but it also shows signs of a complex geological history. There are bright spots on Ceres, deposits of salt and other reflective minerals that may have been left behind by briny water seeping up from beneath the surface. Ceres is thought to contain a large amount of water ice, possibly more fresh water than exists on Earth, locked up in its cold interior. It is a quiet, frozen world, but it holds hints of past activity, maybe even a subsurface ocean at some point in its long history. We do not know for certain, and the details of Ceres's interior and its history are still being studied. Beyond Ceres, there are other large asteroids, though none are round. Vesta, for example, is about 525 kilometers across and has a surface of basaltic rock, similar to the volcanic rocks found on Earth and the Moon. Pallas is about 512 kilometers across and has an orbit that is tilted at a steep angle compared to most of the belt. Hygeia is about 434 kilometers across and is dark and carbon-rich. Each of these large asteroids has its own character, its own shape and composition and history. Some are solid rock, some are loose piles of rubble held together by their own weak gravity. Some are rich in metals like iron and nickel. Some are rich in carbon and organic compounds. They are like a library of the early solar system, preserving the materials that went into building the planets, materials that have long since been melted and mixed and transformed on larger worlds like Earth. The smaller asteroids are even more numerous, and they come in an endless variety of shapes. Because they are so small, their gravity is too weak to pull them into spheres, so they remain irregular, lumpy, often looking like potatoes or peanuts or strange, twisted sculptures. Many of them are covered in craters, the marks of ancient collisions. Some have tiny moons of their own, small companions that orbit them in a slow, mutual dance. The surfaces of these asteroids have never been weathered by wind or water. They are exactly as they have been for billions of years, silent witnesses to the earliest days of the solar system. When we study meteorites that have fallen to Earth, many of them are pieces of asteroids, chipped off in collisions and sent on long, slow journeys that eventually ended in our atmosphere. Holding a meteorite is holding a piece of the asteroid belt, a fragment of a world that never was. The asteroids are not evenly distributed throughout the belt. There are gaps and clusters, shaped by the gravity of Jupiter. These are called Kirkwood gaps, and they occur at distances from the Sun where an object's orbit would be a simple fraction of Jupiter's orbit. Objects in these gaps would feel a regular, rhythmic tug from Jupiter, which over time would pull them out of those orbits. So the gaps are mostly empty, swept clean by the giant planet's influence. There are also groups of asteroids that share similar orbits, called families, which are thought to be the fragments of larger bodies that were broken apart in ancient collisions. These families drift together, slowly spreading out over millions of years, but still bearing the orbital signature of their common origin. The temperature in the asteroid belt is cold. At this distance from the Sun, the sunlight is much weaker than it is on Earth. The average surface temperature of an asteroid is well below freezing, perhaps -70 degrees Celsius, or even colder. The Sun appears as a bright star, not a disk, and the sky is utterly black even during the day. There is no atmosphere on any asteroid, no wind, no sound. Each one is a world of absolute silence, its only motion the slow spin on its axis and the steady, patient progress of its orbit around the Sun. Some asteroids tumble, their rotation axis wobbling in complex ways, the result of ancient impacts that set them spinning. Others rotate smoothly, their long axis pointing steadily in one direction. Each one is a small, self-contained universe, following its own quiet path through the void. As we drift through the asteroid belt now, we do not see a dense field of rocks. We see, instead, a scattering of faint lights, far apart and slow-moving, like distant ships on a dark sea. Every so often, an asteroid comes close enough to see as more than a point, a small, irregular shape passing silently by. Then it recedes, growing smaller and dimmer, until it is indistinguishable from the background stars. The belt is a region of transition. Behind us lie the rocky inner worlds, small and warm and solid underfoot. Ahead of us lies the realm of the giants, planets so large that they blur the line between world and star. Jupiter is the first of these, and its presence is already felt, even here, in the gravitational rhythms that have shaped the belt for billions of years. We are approaching Jupiter now, the king of the planets, a world of swirling clouds and ancient storms, a world so large that it could swallow all the other planets combined. But we are not in a hurry. The asteroid belt stretches on around us, quiet and patient, and we drift through it at a pace that matches the slow, steady orbits of the asteroids themselves. There is no rush. The solar system has been here for billions of years, and it will be here for billions more. We can take our time, moving slowly outward, letting the silence and the darkness and the scattered, gentle light of the asteroids ease us farther into the deep, restful quiet of the outer solar system. Jupiter waits ahead, vast and calm, and we will reach it soon enough. For now, let the stillness of the belt hold you, a quiet interlude between the familiar rocks of home and the great gas giants that lie beyond. The stillness of the asteroid belt slowly falls behind us now, that quiet scattering of rocky bodies continuing their patient, ancient orbits in the dark. Ahead, the character of space begins to change. We are entering the realm of the giants, the outer solar system, where the planets are no longer small, solid worlds of rock and metal, but enormous spheres of gas and liquid, swirling with bands of color and surrounded by families of moons. The first of these giants, and by far the largest, is Jupiter. It has been visible to us for a long time as we drifted outward, a bright, steady point of light growing slowly larger. Now, as we draw closer, its true scale begins to reveal itself, and it is a scale that is difficult to hold in the mind. Jupiter is the largest planet in the solar system. To say that it is large is to understate the matter almost completely. Jupiter is so massive that it contains more than twice the mass of all the other planets combined. If you took Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, and placed them all on one side of a scale, and put Jupiter on the other side, Jupiter would still outweigh them by a significant margin. Its diameter at the equator is about 143,000 kilometers. That is more than 11 times the diameter of Earth. If Jupiter were a hollow shell, you could fit more than 1,300 Earths inside it. It is a world of truly staggering proportions, a king among planets, dominating its region of the solar system with a gravity so strong that it shapes the orbits of everything around it, including, as we have seen, the asteroid belt itself. Jupiter is not a rocky world like the ones we have visited so far. It has no solid surface to stand on, no crust or mantle or ground beneath your feet. Jupiter is a gas giant, a term that describes its composition perfectly. It is made almost entirely of hydrogen and helium, the two lightest and most common elements in the universe. In this way, Jupiter is more like the Sun than like Earth. The outer layers of the planet are gas, mostly molecular hydrogen, the same kind of hydrogen we use in fuel cells and balloons. But as you go deeper, the pressure increases enormously. The hydrogen gas becomes denser and denser, compressed by the weight of all the material above it. At some depth, the hydrogen is no longer a gas, but a liquid, a strange metallic form of liquid hydrogen that conducts electricity like a metal. Deeper still, there is likely a core, but it is not a solid, rocky core like Earth's. It is probably a dense, hot mixture of heavier elements and possibly a form of metallic hydrogen, though the exact nature of Jupiter's core is still uncertain and actively studied. The conditions inside Jupiter are so extreme that they are difficult to replicate in laboratories. So much of what we know comes from models and calculations, which are always being refined. The atmosphere of Jupiter, the part we can see from space, is a place of constant, slow motion. It is organized into bands of color that run parallel to the equator, alternating between light zones and dark belts. The light zones are regions of rising gas, where clouds of ammonia ice form high in the atmosphere. The dark belts are regions of sinking gas, where the clouds are thinner and we can see deeper into the planet. These bands circle the entire globe, and they are broken here and there by storms and eddies and swirling ovals of various sizes. The whole planet rotates very quickly. A day on Jupiter lasts only about 10 hours. That rapid spin stretches the atmosphere into these parallel bands and gives the planet its slightly flattened shape, wider at the equator than at the poles. If you watched Jupiter over time, you would see the bands slowly shifting, changing color and intensity, merging and separating in a slow, fluid dance. The most famous feature on Jupiter is a storm, a giant, swirling anticyclone known as the Great Red Spot. It has been observed for centuries, since at least the time of Galileo, and possibly even earlier. The Great Red Spot is larger than the entire Earth. It is an oval of reddish, swirling clouds, rotating counterclockwise, completing a full turn about once every 6 Earth days. The winds around its edges reach speeds of several hundred kilometers per hour. Why the spot is red is not fully understood. The color may come from compounds of phosphorus or sulfur, or from complex organic molecules that are broken apart by ultraviolet light from the sun and then recombine in the upper atmosphere. But this is still a matter of research and debate. What we do know is that the Great Red Spot is very, very old, and it has persisted while smaller storms come and go around it. Recently, the spot has been observed to be shrinking slightly, and its shape is changing. Whether it will one day disappear entirely, or whether it will stabilize and continue for centuries more, is something that no one can say with certainty. It is a quiet reminder that even the most permanent-looking features of the universe are, on long enough timescales, subject to change. Jupiter has a very strong magnetic field, the strongest of any planet in the solar system. It is generated by the movement of the metallic hydrogen deep in the planet's interior. This magnetic field is about 20,000 times stronger than Earth's, and it extends far out into space, creating a magnetosphere that is enormous. If the magnetosphere were visible from Earth, it would appear larger than the full moon in the sky, even though Jupiter itself is so far away. This magnetic field traps charged particles from the solar wind and from Jupiter's own moons, creating intense radiation belts that would be very dangerous to any unprotected spacecraft or astronaut. The radiation near Jupiter is one of the main challenges that engineers must deal with when designing missions to explore this giant world and its surroundings. Jupiter also has the most known moons of any planet in the solar system. At last count, the number of confirmed moons is 95, though that number may change as more small moons are discovered. Most of these are tiny, irregular objects, only a few kilometers across, and they are likely captured asteroids or fragments of larger collisions. But a few of Jupiter's moons are worlds in their own right, large and complex and fascinating. They are often called the Galilean moons, after Galileo Galilei, who first observed them through his telescope in the year 1610. Their names are Io, Europa, Ganymede, and Callisto. Each one is different, each one has its own story, and we will spend time with them in the next part of our journey, drifting closer to examine their quiet, strange surfaces. From Jupiter, the Sun appears about 5 times smaller in the sky than it does from Earth. The sunlight here is much weaker, only about 4% as bright as what we experience on our own planet. The outer solar system is a cold, dim place compared to the warm, bright inner regions where the rocky planets orbit. And yet, Jupiter itself generates some of its own heat. The planet is still slowly contracting, releasing gravitational energy as it shrinks by a tiny amount each year. This internal heat drives the weather and keeps the atmosphere dynamic. In fact, Jupiter radiates more heat into space than it receives from the Sun. It is a world that glows faintly in the infrared, a warm giant in the cold dark. As we drift past Jupiter now, we can see its system of rings, though they are very faint and difficult to observe. Jupiter's rings are made mostly of dust, not ice, like Saturn's famous rings, and they were not discovered until the Voyager spacecraft flew by in 1979. They are thin and dark, likely formed from material knocked off Jupiter's inner moons by micrometeorite impacts. They are a subtle feature, easy to miss, but they add a quiet, delicate beauty to the planet as it turns in the darkness. Jupiter orbits the Sun at an average distance of about 778 million kilometers, which is more than 5 times Earth's distance. A single year on Jupiter, one full orbit around the Sun, takes about 12 Earth years, so the seasons on Jupiter are long and slow, though because the planet has very little axial tilt, the seasonal changes are minor compared to the constant turmoil of the atmosphere. Jupiter just keeps turning, its bands of cloud flowing endlessly, its storms swirling and merging, its moons circling in their silent paths. It has been doing this for more than 4 billion years, and it will continue doing it for billions more. It is a steady, stable presence, a gravitational anchor for the entire outer solar system. As we prepare to leave Jupiter and continue our journey outward, we will first take a closer look at those 4 large moons, the Galilean satellites. They are worlds of fire and ice, of hidden oceans and ancient surfaces, and they deserve their own quiet moment of attention. So we will pause here, near Jupiter, and drift among its moons, letting the slow, steady light of the giant planet wash over us as we explore these smaller, stranger worlds that circle it. The journey is long, and there is no need to hurry. Jupiter will wait, its bands of cloud flowing in slow motion, its great red spot turning patiently in the southern hemisphere, a quiet giant keeping watch over its family of moons as we drift closer to them, one by one. We pause here, near Jupiter, letting the slow, steady light of the giant planet wash over us as we explore the smaller, stranger worlds that circle it. Jupiter, with its bands of cloud flowing in slow motion and its great red spot turning patiently in the southern hemisphere, is a quiet giant keeping watch over a family of moons that is both large and wonderfully diverse. Most of Jupiter's moons are tiny, irregular bodies, captured asteroids or fragments of ancient collisions, but 4 of them stand apart. These are the Galilean moons, so named because they were first observed by the astronomer Galileo Galilei in the year 1610, when he pointed his small telescope at Jupiter and saw 4 points of light arranged in a line around the planet. That observation changed our understanding of the universe, showing that not everything orbits the Earth. Today, these 4 moons are known to be worlds in their own right, each with its own personality, its own history, and its own quiet mysteries. We will visit each one now, drifting closer to them one by one, taking our time. The innermost of the 4 large moons is Io. It orbits very close to Jupiter, at a distance of about 422,000 kilometers, which is only slightly farther than our own moon orbits Earth. But the similarity ends there. Io is a world of fire. It is the most volcanically active body known anywhere in the solar system. Its surface is dotted with hundreds of volcanoes, many of them actively erupting at any given time. These eruptions send plumes of sulfur and sulfur dioxide gas, shooting hundreds of kilometers into the black sky before the material falls back to the surface, coating the ground in vivid shades of yellow, orange, red, and white. Io looks, from a distance, like a pizza or a moldy orange, its surface a mottled patchwork of volcanic deposits and lava flows. There are no impact craters on Io, because the constant volcanic activity buries any craters almost as soon as they form. The surface is always young, always being remade. The reason for all this volcanic activity is a phenomenon called tidal heating. Io is caught in a gravitational tug-of-war between Jupiter and the other large moons, especially Europa and Ganymede. Their combined gravity pulls on Io, stretching and squeezing it as it moves in its orbit. This constant flexing generates enormous amounts of heat inside the moon, melting the rock and creating magma that erupts onto the surface. Io is essentially a giant ball of rock being kneaded like dough, and the heat from that kneading powers its volcanoes. The surface temperature of Io is very cold in most places, around -130 degrees Celsius, but near the volcanic vents it can reach over 1,600 degrees. It is a world of extremes, fire and ice existing side by side in the quiet dark of the outer solar system. Drifting outward from Io, we come to Europa. Europa is a very different kind of world. It is covered in ice. Its surface is smooth and bright, with very few craters, and it is crisscrossed by a network of dark, reddish-brown lines that look like cracks in an eggshell. These lines are ridges and fractures where the ice has broken apart and refrozen. Europa's surface is one of the smoothest and youngest in the solar system, geologically speaking, which suggests that something is resurfacing it over time. Beneath the icy crust, scientists think there is a liquid water ocean. This has not been directly confirmed by seeing the ocean with our own instruments, but the evidence for it is strong. Measurements of Europa's magnetic field, the way it interacts with Jupiter's magnetosphere, and the patterns of cracks on its surface all point to the presence of a salty, liquid ocean beneath the ice, kept warm by the same kind of tidal heating that powers Io's volcanoes, though to a much milder degree. If Europa does have a liquid water ocean, and if that ocean has been there for billions of years, then it is one of the most intriguing places in the solar system to search for life. On Earth, wherever we find liquid water, we find life. Deep ocean vents, far from sunlight, are teeming with organisms that survive on chemical energy from the Earth's interior. It is possible, though not proven, that similar conditions could exist on Europa, but we must be careful not to assume too much. No direct evidence of life on Europa has been found, and the ocean itself, if it exists, has never been seen. Future missions are being planned to explore Europa more closely, to fly through the plumes of water vapor that seem to erupt from its surface, and perhaps one day to land on its ice and drill down to whatever lies beneath. For now, Europa remains a quiet, bright mystery, a smooth pearl of ice hanging in the darkness, keeping its secrets close. Moving farther out, we come to Ganymede. Ganymede is the largest moon in the solar system. It is even larger than the planet Mercury, with a diameter of about 5,268 kilometers. If Ganymede orbited the Sun directly, it would be classified as a planet. Its surface is a mix of two types of terrain. There are dark, heavily cratered regions that are very old, and lighter, grooved regions that are younger and were formed by tectonic activity. Ganymede has its own magnetic field, a tiny version of the ones that Earth and Jupiter generate, which is something no other moon in the solar system has. This magnetic field is generated by a liquid iron core deep inside Ganymede, another sign that this moon is a complex, layered world. There is also evidence that Ganymede, like Europa, may have a liquid water ocean beneath its surface, though it would be deeper down and sandwiched between layers of ice. Ganymede is a quiet, ancient world, its surface a record of billions of years of history, its interior still warm enough to keep a magnetic field alive. The outermost of the four large moons is Callisto. Callisto is about the same size as Mercury, just slightly smaller than Ganymede, with a diameter of about 4,821 kilometers. Its surface is one of the oldest and most heavily cratered in the entire solar system. Every square kilometer of Callisto is pocked with impact craters, many of them overlapping, some of them surrounded by faint rings of ejecta. There are no large mountains, no volcanoes, no signs of tectonic activity. Callisto is a world that has been geologically dead for most of its history. It simply orbits Jupiter, its surface accumulating craters, untouched by the internal forces that shape so many other worlds. There is also evidence that Callisto may have a subsurface ocean, but if it does, it is very deep and very old, and it does not seem to have broken through the surface in the way that Europa's features suggest. Callisto is a place of profound stillness, a frozen museum of the early solar system, unchanged for eons. These four moons, Io, Europa, Ganymede, and Callisto, are often called the Galilean satellites, and they are a solar system in miniature. Each one is different. Each one tells a different part of the story of how worlds form and evolve. They are bound to Jupiter, circling it in a regular, predictable pattern. Io, Europa, and Ganymede are locked in what is called a Laplace resonance, a gravitational relationship in which their orbital periods are simple ratios of each other. For every 4 orbits that Io completes, Europa completes 2, and Ganymede completes 1. This resonance is what drives the tidal heating that keeps Io volcanic and Europa's ocean liquid. It is a slow, steady rhythm, a clockwork of worlds that has been ticking for billions of years. As we drift among these moons, we can see Jupiter looming in the sky above them, a vast, banded presence that dominates the view. From Io, Jupiter would appear about 36 times larger in the sky than our moon appears from Earth. It would be a breathtaking sight, though there would be no one there to see it, except perhaps the silent volcanoes and the endless lava plains. From Callisto, Jupiter would be smaller, but still enormous, a constant companion in the black sky. The sunlight out here is weak, only a fraction of what we receive on Earth, and the surfaces of these moons are cold and quiet. But they are not dead. They are alive with slow processes, with the flex of tidal forces, with the slow churn of internal heat, with the patient march of craters accumulating over billions of years. We have spent a quiet time here among Jupiter's moons, getting to know them, letting their stillness and their strangeness settle into the background of our journey. But we cannot stay forever. The solar system is large, and there are more worlds ahead. The next planet we will visit is, in many ways, the most beautiful of them all. It is Saturn, a world encircled by a dazzling system of rings, a planet of pale gold and gentle light. Its moons are just as fascinating as Jupiter's, and one of them, Titan, has a thick atmosphere and lakes of liquid methane. We will drift toward Saturn now, leaving Jupiter and its family of moons behind, but carrying with us the memory of their quiet, patient faces, turning slowly in the dark. We drift onward now, leaving Jupiter and its family of moons behind, carrying with us the memory of their quiet, patient faces, turning slowly in the dark. Ahead of us, the next planet waits, and it is a world that many people think of as the most beautiful in the solar system, Saturn. Even at a great distance, it is unmistakable. No other planet looks quite like it. The rings set it apart, a vast, flat system of icy particles that encircles the planet like a delicate halo. Saturn has been known since ancient times, but its rings were not clearly seen until Galileo first pointed his telescope at the sky, and even he could not understand what he was looking at. He thought Saturn had ears, or perhaps two smaller planets attached to its sides. It took later astronomers with better telescopes to realize that what they were seeing was a system of rings, thin and bright, completely unlike anything else known. Saturn is the second largest planet in the solar system, after Jupiter. Its diameter at the equator is about 120,000 kilometers, about 9.5 times the diameter of Earth. Like Jupiter, Saturn is a gas giant, made mostly of hydrogen and helium, with no solid surface to stand on. The outer layers are gas, the deeper layers are liquid, and at the center there is probably a dense core of heavier elements, perhaps rocky or metallic, though the details of Saturn's interior are still studied and not fully settled. Saturn is famous for being the least dense of all the planets. In fact, its average density is less than that of water. If you could find a bathtub large enough to hold Saturn, the planet would float. This is a gentle, almost whimsical fact, and it speaks to the light, airy nature of this giant world, a world that seems to float in space as easily as a cloud floats in a summer sky. The rings are the main attraction, and they deserve a long, slow look. Saturn's ring system is made mostly of ice particles, with some rock mixed in. These particles range in size from tiny grains, no larger than a speck of dust, to large chunks as big as a house or a small mountain. They are all orbiting Saturn in a flat plane, each particle following its own path around the planet. From a distance, the rings look solid, like a smooth disk of light. But this is an illusion. If you were to fly through the rings, you would find them to be mostly empty space, with the particles scattered far apart. The rings are not a single, solid object. They are divided into several major sections, separated by gaps. The main rings are named, in order of their discovery, the D ring, the C ring, the B ring, the A ring, and the F ring, with the B ring being the brightest and most massive. The most famous gap is the Cassini division, a dark, empty band between the A and B rings, named after the astronomer Giovanni Cassini, who first observed it in the year 1675. Why are the rings there? This is a question that is not fully answered. One idea is that the rings are the remains of a moon or a comet that came too close to Saturn and was torn apart by the planet's gravity. Another idea is that they are leftover material from the formation of Saturn itself, material that never came together to form a moon because it was too close to the planet and the tidal forces were too strong. It is possible that the rings are relatively young, perhaps only a few 100 million years old, and that they will not last forever. Over time, the ring particles slowly spiral inward toward the planet, raining down into the atmosphere. The rings may gradually disappear, their bright, icy material absorbed into the bulk of Saturn. This is a slow process, measured in tens or hundreds of millions of years, and for now the rings remain, a breathtaking sight, a quiet reminder of the impermanence of even the most beautiful things. The rings are not the only feature that makes Saturn beautiful. The planet itself is a pale, golden color, with faint bands of cloud that are similar to Jupiter's but much more subtle. Saturn's atmosphere is hazy with ammonia ice, which gives it a softer, more muted appearance than its larger sibling. Saturn also rotates quickly, completing a day in about 10.5 hours, and this rapid spin flattens the planet at the poles and stretches it at the equator. Saturn is the most flattened planet in the solar system, with its equatorial diameter noticeably larger than its polar diameter. If you could look at it from above the pole, it would appear almost perfectly round, but from the side, it is visibly squashed, a gentle oval shape. Saturn has a strong magnetic field, though it is weaker than Jupiter's, and it generates its own internal heat, though again, less intensely than Jupiter. The heat comes from a process called helium rain. Deep inside Saturn, the pressure is so great that helium condenses into droplets and falls toward the core, releasing gravitational energy as it goes. This slow, steady rain of helium, deep within the planet, has been going on for billions of years, and it keeps Saturn warmer than it would otherwise be, given its distance from the Sun. Saturn orbits the Sun at an average distance of about 1.4 billion kilometers, which is nearly 10 times Earth's distance. From Saturn, the Sun appears about 10 times smaller in the sky than it does from Earth, and the sunlight is only about 1% as bright. A year on Saturn, one full orbit around the Sun, takes about 29.5 Earth years. The seasons on Saturn are long and slow, each one lasting more than 7 Earth years. Because Saturn has a significant axial tilt, similar to Earth's, the rings present a changing view to us as the planet moves through its orbit. Sometimes the rings are tilted wide open, showing their full glory. Sometimes they appear edge-on, a thin line of light that nearly disappears. These changes happen slowly, over years, a quiet, graceful rhythm that marks the passage of time on the giant world. Saturn has a large and diverse family of moons. Dozens of confirmed moons orbit the planet, and there are likely more waiting to be discovered among the rings. Many of these moons are small, irregular objects, but a few are large and remarkable worlds. The most famous is Titan, Saturn's largest moon. Titan is the second largest moon in the solar system after Ganymede, and it is larger than the planet Mercury. What makes Titan special is its atmosphere. It is the only moon in the solar system with a thick atmosphere, and that atmosphere is mostly nitrogen, like Earth's, with a small amount of methane. The atmospheric pressure at Titan's surface is about 1.5 times Earth's, so if you stood on Titan, you would feel a pressure similar to what a diver feels a few meters underwater. The surface is hidden beneath an orange haze, a smog of complex organic molecules created when sunlight breaks apart methane and the fragments recombine. But beneath that haze, Titan has a landscape that is strangely familiar. There are mountains, dunes, and river channels. There are lakes and seas, but they are not filled with water. They are filled with liquid methane and ethane, which are gases on Earth but liquids at the cold temperatures of Titan, where the surface temperature is about -179 degrees Celsius. Titan has a hydrological cycle, with methane rain, methane rivers, and methane lakes, a kind of cold, alien mirror of Earth's own water cycle. It is a quiet, strange world, and it is one of the most fascinating places in the solar system. Another notable moon is Enceladus, a small, icy moon that has become a subject of great interest. Enceladus has a surface of bright, fresh ice, and at its south pole, geysers of water vapor and ice particles shoot out into space. These plumes come from a subsurface ocean of liquid water, which has been confirmed by multiple lines of evidence. Enceladus is another place where the conditions for life as we know it, liquid water, chemical energy, and organic molecules, may exist, though whether life actually exists there is completely unknown and unconfirmed. The plumes of Enceladus feed material into one of Saturn's rings, the E-ring, creating a faint, diffuse band that surrounds the planet. There are many other moons, each with its own quiet story. Mimas has a giant crater that makes it look like the Death Star from a famous movie. Iapetus has one side that is bright white and another side that is dark as coal, a contrast that has puzzled astronomers for centuries. Hyperion is a tumbling, sponge-like object, chaotically rotating. Rhea, Dione, Tethys, each one a small world of ice and rock, each one following its own patient orbit. Saturn's moons are like a miniature solar system, and they interact with the rings in complex ways, their gravity sculpting gaps and waves in the ring material, a slow dance of ice and gravity that has been going on for eons. As we drift past Saturn, we can see the rings stretching out in all their quiet glory, a pale golden disk of scattered light. The planet itself glows softly, its bands of cloud shifting slowly, its storms coming and going. The whole system has a calm, serene beauty, a sense of gentle order. There is no violence here, no chaos, just the slow turning of rings and moons, the steady fall of helium rain deep inside the planet, and the quiet light of a distant sun washing over everything. It is a good place to pause, to let the peace of Saturn's quiet rings settle into your mind as you drift deeper into rest. From Saturn, we will continue our journey outward. The next worlds we will meet are different from the gas giants. They are smaller, colder, and stranger in their own quiet ways. They are the ice giants, Uranus and Neptune, worlds of deep blue and pale green, tilted and windswept, waiting for us in the far reaches of the solar system. But for now, let Saturn hold your attention, its rings spread wide, its moons circling patiently, a quiet heart of the outer solar system, beating slowly in the dark. Saturn fades slowly behind us now, its rings still spread wide, its moons still circling patiently, a quiet heart of the outer solar system beating slowly in the dark. We drift farther out, into a region where the sun is no longer a bright disk, but merely the brightest star in the sky, a point of light that casts only a dim, cold glow. Out here, the worlds are different. They are not the massive gas giants like Jupiter and Saturn. They are smaller, colder, and composed of different materials. They are called the ice giants, and the first of them we meet is Uranus. Uranus is the seventh planet from the Sun, orbiting at an average distance of about 2.9 billion kilometers. That is roughly 19 times farther from the Sun than Earth is. Light from the Sun takes about 2 hours and 40 minutes to reach Uranus. To put that in perspective, when sunlight leaves the Sun, it passes Earth in 8 minutes, passes Jupiter in about 43 minutes, passes Saturn in about an hour and a half, and then travels for nearly another hour through the empty dark before finally arriving at Uranus. The sunlight here is weak and pale, only about 1/400th as bright as it is on Earth. A day on Uranus is about 17 hours long, but a year, one full orbit around the Sun, takes about 84 Earth years. If you were born on Uranus, you would never live to see your first birthday, at least not in Uranian years. The seasons here are long and strange, each one lasting 21 Earth years, a slow, patient turning through the cold. Uranus was the first planet to be discovered with a telescope. Mercury, Venus, Mars, Jupiter, and Saturn are all visible to the naked eye and have been known since ancient times. But Uranus is too dim to be seen without help. It was discovered in the year 1781 by the astronomer William Herschel, who initially thought it might be a comet. Once its orbit was calculated, it became clear that it was a new planet, the first to be added to the known roster since antiquity. Herschel wanted to name it Georgium Sidus, after King George III of England, but the name did not stick. Instead, it was given the name Uranus, after the ancient Greek god of the sky, a fitting name for a world so distant and serene. Uranus is classified as an ice giant, which distinguishes it from the gas giants Jupiter and Saturn. The difference is mostly in what the planets are made of. Jupiter and Saturn are mostly hydrogen and helium, with only small amounts of heavier materials. Uranus, by contrast, is made largely of water, ammonia, and methane ices, surrounding a small rocky core. These are not ices in the everyday sense of frozen water. They are superheated, dense fluids, existing at high pressures and temperatures deep within the planet. But in planetary science, The term ice refers to these volatile compounds, and they make up a much larger fraction of Uranus than they do of Jupiter or Saturn. This gives Uranus a different character, a different color, and a different internal structure. The atmosphere of Uranus is mostly hydrogen and helium, but it contains a significant amount of methane. Methane is the molecule that gives Uranus its distinctive color. Methane absorbs red light and reflects blue and green light, so when sunlight hits the planet, the red part of the spectrum is absorbed and the blue-green part bounces back. The result is a pale, soft cyan, a cool, gentle hue that makes Uranus look like a smooth, polished marble of ice. The atmosphere is relatively featureless compared to Jupiter and Saturn. There are faint bands and occasional small storms, but they are subtle and often invisible without advanced telescopes. Uranus has a quiet, serene appearance, a world that seems to be at peace with its own cold isolation. But Uranus has one feature that sets it apart from every other planet in the solar system. It is tilted on its side. While most planets rotate with their axes more or less upright relative to the plane of their orbits, Uranus is tilted at an angle of about 98 degrees. That means it essentially rolls around the Sun on its side, with its poles pointing roughly where other planets have their equators. From our perspective, Uranus looks like a target, with its rings and moons circling it vertically, while the planet itself seems to be lying down. This extreme tilt has a profound effect on the seasons. For half of its orbit, which is 42 Earth years, one pole faces the Sun directly, while the other pole is in complete darkness. Then, as the planet moves to the other side of its orbit, the situation reverses. The Sun shines on the other pole for another 42 years. Each pole experiences a day that lasts for decades, followed by a night that lasts just as long. It is a slow, extreme rhythm, unlike anything on the other planets. Why is Uranus tilted in this way? The leading idea, though it is not proven, is that early in its history, Uranus was struck by one or more large objects, perhaps protoplanets the size of Earth or larger. These collisions could have knocked the young planet over, leaving it spinning on its side. This would have been a violent event, but it happened billions of years ago, and since then, Uranus has settled into its tilted, rolling orbit, calm and steady. There is a quiet, gentle irony in this. A world that was once the site of immense violence is now one of the most placid-looking planets in the solar system. Uranus has a system of rings, though they are nothing like Saturn's. The rings of Uranus are dark, narrow, and faint. They were discovered by accident in the year 1977, when astronomers watched Uranus pass in front of a distant star and noticed that the star's light flickered several times before and after the planet itself blocked it. These flickers were caused by the rings, thin bands of dark material that orbit close to the planet. There are 13 known rings, made mostly of dark, rocky particles, possibly with some ice. They are not bright and glorious like Saturn's rings. They are subtle, almost secretive, a quiet detail that rewards close attention. Uranus has a family of moons, 27 known at current count. Most of them are small, irregular objects, but a few are larger and more interesting. The largest moons of Uranus are Miranda, Ariel, Umbriel, Titania, and Oberon. Their names are drawn not from Greek or Roman mythology, as is common for planets, but from the works of William Shakespeare and Alexander Pope. This gives the Uranian system a literary, almost whimsical quality. Titania is the largest, about 1,578 kilometers in diameter, less than half the size of our own moon. Oberon is slightly smaller. Miranda is the smallest of the 5 major moons, but perhaps the most intriguing. Its surface is a patchwork of very different terrains, with deep canyons, scarps, and strange oval-shaped features called coronae. The surface looks as though it was broken apart and reassembled, a jumbled, chaotic landscape that hints at a violent past. The reason for Miranda's strange appearance is not fully understood, but it adds a quiet mystery to this small, distant moon. The other moons of Uranus are similarly cold and quiet. They are made of a mixture of rock and ice, and their surfaces are heavily cratered, showing their great age. They are dark, reflecting only a small amount of the dim sunlight that reaches them. They orbit Uranus in the same tilted plane as the planet's equator, meaning they follow paths that are nearly perpendicular to the plane of the solar system. From these moons, Uranus would appear as a large, pale blue-green disk, its rings barely visible, its atmosphere smooth and serene, hanging in the black sky. As we drift past Uranus now, we can see it rolling along in its orbit, tilted and quiet, its pale cyan light casting no warmth. It is a world of slow, patient rhythms, where the seasons last for decades and the sun is just a bright star. There is no drama here, no great storms or volcanic eruptions, just the steady, gentle passage of time, the slow turning of the rings, the quiet orbit of the moons. Uranus does not demand attention the way Jupiter or Saturn does. It simply is, a cool, serene presence at the edge of the known planets. From Uranus, we will continue our journey outward to the last of the full planets, a world that is similar in many ways to Uranus but different in others. It is Neptune, the most distant known planet from the Sun, a world of deep blue and the fastest winds in the solar system. It waits for us in the darkness beyond, a final stop before we leave the realm of the planets entirely and drift into the quiet, scattered regions at the very edge of the Sun's influence. But there is no hurry. The night is long, and the solar system is patient. For now, let Uranus recede slowly behind us, a pale, tilted pearl in the vast black sea of space, turning gently, quietly, on its long, slow march around the distant sun. Uranus recedes slowly behind us now, a pale, tilted pearl in the vast black sea of space, turning gently, quietly, on its long, slow march around the distant sun. We drift farther still, into the cold and the dark, toward the last planet that we know of in the solar system, Neptune. It is the 8th planet from the Sun, and it orbits at an average distance of about 4.5 billion kilometers. That is 30 times farther from the Sun than Earth is. Light from the Sun takes about 4 hours to reach Neptune. To put that in perspective, when you step outside on a sunny day and feel the warmth on your skin, that warmth is 8 minutes old. The light that falls on Neptune, faint and cold, began its journey 4 hours earlier. The Sun, from Neptune, is not a disk. It is just a very bright star, the brightest star in the sky, but a star nonetheless, a point of light in an endless black sea. Neptune was discovered in a way that was different from any planet before it. After Uranus was found, astronomers tracked its orbit carefully, and they noticed something strange. Uranus was not moving exactly as the laws of gravity predicted. It was being tugged, ever so slightly, by something else, something unseen. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where this unseen object should be, based on the way it was pulling on Uranus. In the year 1846, the astronomer Johann Galle pointed his telescope at the spot Le Verrier had predicted, and there it was, Neptune. It was the first planet to be found not by chance observation, but by the power of mathematics, by the quiet, patient work of the human mind, tracing the invisible threads of gravity. It was a triumph of science, and it added a new, deep blue world to the family of planets. Neptune is similar in many ways to Uranus. It is also an ice giant, made largely of water, ammonia, and methane ices surrounding a small rocky core. Its atmosphere is mostly hydrogen and helium, with a significant amount of methane. And it is that methane, once again, that gives the planet its color. Methane absorbs red light and reflects blue light, and on Neptune, the blue is deeper and more vivid than on Uranus. Neptune is a rich, striking cobalt, a jewel tone that seems to glow against the blackness of space. The reason for the deeper blue is not entirely settled, but it may have to do with additional trace compounds in the atmosphere or with differences in the way the methane is distributed. Whatever the cause, Neptune is a beautiful world, a deep blue marble hanging in the farthest reaches of the planetary system. Neptune is slightly smaller than Uranus in diameter, about 49,500 kilometers across, but it is slightly more massive. Its gravity is a little stronger, and its internal heat is a little greater. In fact, Neptune radiates more than twice as much heat as it receives from the Sun. Like Jupiter and Saturn, Neptune has its own internal heat source, the slow release of gravitational energy left over from its formation billions of years ago. This internal heat drives the weather on Neptune, and the weather on Neptune is unlike anything on the other ice giant. Uranus is calm and relatively featureless. Neptune is active, with clouds and storms and the fastest sustained winds of any planet in the solar system. The winds on Neptune can reach speeds of over 2,000 kilometers per hour. That is faster than the speed of sound in Earth's atmosphere. These winds whip the clouds into long, bright streaks and dark spots that come and go over time. When the Voyager 2 spacecraft flew by Neptune in the year 1989, it observed a giant storm called the Great Dark Spot, a swirling anticyclone similar to Jupiter's Great Red Spot but more short-lived. The Great Dark Spot was about the size of Earth, and it churned in Neptune's southern hemisphere, surrounded by bright, wispy clouds of methane ice. When the Hubble Space Telescope looked at Neptune a few years later, the Great Dark Spot was gone. New dark spots have appeared since then, in different places, at different sizes. Neptune's weather is dynamic and changeable, a quiet reminder that even in the cold outer reaches, there is motion and change and the slow, steady flow of energy. A day on Neptune lasts about 16 hours. The planet rotates quickly, and like Jupiter and Saturn, its rapid spin flattens it slightly at the poles and stretches it at the equator. A year on Neptune, however, is very, very long. Neptune takes about 165 Earth years to complete one full orbit around the Sun. Since its discovery in 1846, Neptune has only completed one full orbit, in the year 2011. Every human being who has ever seen Neptune through a telescope has seen it at a different point in its long, slow journey. The planet has been quietly following its path for billions of years, and it will continue for billions more, marking time in a way that makes our own lives seem like the briefest of flickers. Neptune has a system of rings, though they are even fainter and darker than those of Uranus. The rings of Neptune are made of dark, rocky material, and they are clumpy and uneven. In some places the rings are thin, and in other places they form arcs, bright clumps of material that persist against the background of the ring. The reason for these arcs is not fully understood, but it likely has to do with the gravitational influence of small moons embedded in or near the rings. The rings are named after astronomers who contributed to the discovery and study of Neptune: Gale, Leverrier, Lassell, Arago, and Adams. They are a subtle feature, easily overlooked, but they add a quiet, delicate beauty to this distant world. Neptune has 14 known moons. The largest of them is Triton, and Triton is one of the strangest and most interesting moons in the solar system. It is large, about 2,700 kilometers in diameter, making it the 7th largest moon overall. Triton is unusual because it orbits Neptune in the opposite direction to the planet's rotation. This is called a retrograde orbit, and it strongly suggests that Triton did not form around Neptune but was captured, a wandering object from the Kuiper Belt that came too close and was pulled into orbit by Neptune's gravity. Triton is cold, one of the coldest places in the solar system, with a surface temperature of about -235 degrees Celsius. Its surface is a mix of frozen nitrogen, water ice, and other ices, and it has features that look like cryovolcanoes, volcanoes that erupt not molten rock but liquid water, ammonia, or methane, which freeze almost instantly in the cold. Triton's surface is relatively young and smooth in places, suggesting that it may still be geologically active. When Voyager 2 flew by, it saw geysers erupting from Triton's surface, dark plumes of nitrogen gas and dust shooting several kilometers into the thin atmosphere before being carried downwind. It was a quiet, ghostly spectacle, a world still alive in the deep freeze of the outer solar system. The other moons of Neptune are much smaller. Proteus is a large, irregularly shaped body, dark and heavily cratered. Nereid has a very stretched-out orbit, another hint of the chaotic past that may have shaped the Neptunian system. The smaller moons are mostly named after water deities from Greek mythology, fitting for a planet named after the god of the sea. They are quiet, dark and cold, following their patient orbits around the deep blue planet. As we drift past Neptune now, we can see it hanging in the darkness, a rich blue disk with faint white wisps of cloud, its rings a barely visible trace, its large moon Triton glowing faintly nearby. Neptune is the last of the full planets we will visit on this journey. Beyond it, there are no more large worlds. There are only the scattered remnants of the solar system's formation, the icy bodies of the Kuiper Belt, and the distant, unseen objects of the Oort Cloud. Pluto waits out there, a small, frozen world that was once considered the ninth planet, now reclassified as a dwarf planet, a member of a vast population of icy bodies that circle the sun in the deep dark. From Neptune, the solar system feels very large and very quiet. The distances between worlds are immense. The sun is barely more than a bright star. The inner planets, Mercury, Venus, Earth, and Mars, are lost in the glare, invisible from this far out. The gas giants, Jupiter and Saturn, are faint points of light, if they are visible at all. And yet, even here, at the edge of the planetary realm, we are still only a tiny fraction of the way to the true edge of the solar system. The Kuiper Belt stretches out beyond Neptune, a wide, flat band of icy debris that includes Pluto and countless other objects. And beyond that, far, far beyond, the Oort Cloud is thought to surround the entire solar system in a vast, spherical shell. We will drift out there soon, into those quiet, distant regions. But for now, let Neptune hold your attention. A deep blue world, windswept and cold, a final sentinel at the edge of the known planets, turning slowly in the dark. Neptune recedes behind us now, that deep blue world, windswept and cold, a final sentinel at the edge of the known planets, turning slowly in the dark. We have left the realm of the full planets behind. Ahead of us lies a different kind of space, a region that is wider, more scattered, and less defined. This is the outer edge of the solar system, where the sun's light is so faint that it barely illuminates the objects that live here, and where the distances between those objects are vast beyond easy comprehension. We are entering the Kuiper Belt, the home of Pluto and countless other icy bodies, and beyond that, the Oort Cloud, a distant shell of frozen objects that marks the very boundary of the sun's influence. Pluto was once considered the ninth planet. For most of the 20th century, schoolchildren learned the names of 9 planets, and Pluto was the last, the smallest, the most distant. It was discovered in the year 1930 by the American astronomer Clyde Tombaugh, who was working at the Lowell Observatory in Arizona. He found it by comparing photographs of the night sky taken several nights apart, looking for a tiny point of light that had moved against the fixed background of stars. That point of light was Pluto, and for decades it was a lonely outlier, the only known world beyond Neptune. But as telescopes improved and astronomers looked more closely, they began to find other objects out there, some of them nearly as large as Pluto, some of them even larger. It became clear that Pluto was not a solitary planet, but one member of a vast population of icy bodies orbiting in the same region. In the year 2006, the International Astronomical Union created a new category of objects called dwarf planets. Pluto was reclassified, not because it had changed, but because our understanding of it had. It was no longer the odd one out. It was the first known member of the Kuiper Belt. Pluto is a small world, about 2,377 kilometers in diameter, which is less than 1/5 the diameter of Earth and smaller than Earth's moon. Its surface is a complex and surprising landscape of mountains, plains, and glaciers. The mountains are made of water ice, which is as hard as rock at the cold temperatures of Pluto, where the surface averages about -230 degrees Celsius. The plains are made of frozen nitrogen, methane, and carbon monoxide, and they show signs of slow glacial flow, meaning the surface of Pluto is being reshaped over time by the movement of ice. There are few craters on some parts of Pluto, which suggests that the surface is relatively young, geologically speaking, perhaps less than 100 million years old. This was a surprise when the New Horizons spacecraft flew past Pluto in the year 2015. A small, cold world so far from the Sun was expected to be geologically dead, its surface ancient and unchanged for billions of years. Instead, Pluto showed signs of recent activity, a quiet, frozen dynamism that no one had predicted. Pluto has a thin atmosphere, made mostly of nitrogen, with traces of methane and carbon monoxide. This atmosphere is only present when Pluto is closer to the Sun in its orbit. Pluto's orbit is quite stretched out, not a neat circle like most of the planets, but an ellipse that brings it closer to the Sun than Neptune at its nearest point, and much farther out at its farthest. When Pluto is closer, the Sun's weak warmth is enough to vaporize some of the surface ices, creating a thin, temporary atmosphere. When Pluto moves farther away, the atmosphere freezes and falls back to the surface as frost. It is a slow, seasonal cycle, but the seasons on Pluto are measured not in months but in decades, each phase of its orbit taking about 124 Earth years to complete. Pluto has 5 known moons. The largest is Charon, and Charon is so large relative to Pluto that the two are sometimes considered a double dwarf planet system. Charon is about 1,200 kilometers in diameter, roughly half the size of Pluto itself. The two orbit a common center of gravity that lies outside Pluto's surface, so they both move around a point in the space between them. Charon's surface is darker and more heavily cratered than Pluto's, with a large reddish polar cap that is thought to be made of organic compounds. The other 4 moons are tiny, irregularly shaped, and orbit farther out. Their names are Styx, Nix, Kerberos, and Hydra. They are small and faint, each one a tiny speck of ice and rock, circling the quiet double world of Pluto and Charon. Pluto is not alone in the Kuiper Belt. The belt is a wide, flat band of icy bodies that stretches from about 30 astronomical units to about 50 astronomical units from the Sun. It contains millions of objects, ranging from small chunks of ice to large dwarf planets. Eris is one of the largest known objects in the Kuiper Belt. It is slightly smaller than Pluto but more massive, and its discovery in the year 2005 was one of the events that led to the reclassification of Pluto. Eris has a single known moon, Dysnomia, and it orbits even farther out than Pluto, taking about 558 Earth years to complete one trip around the Sun. Makemake is another dwarf planet, about 2/3 the size of Pluto, with a reddish surface covered in methane ice. Haumea is a dwarf planet with an unusual elongated shape, spinning so fast that it has stretched itself into a kind of football shape, and it is surrounded by a ring and 2 small moons. There are many others with names like Quaoar, Sedna, Orcus, Varuna, each one a small, frozen world, each one following its own quiet orbit in the deep dark. The Kuiper Belt is thought to be the source of many of the short-period comets that occasionally visit the inner solar system. These comets are icy bodies that have been nudged out of their orbits by gravitational interactions, perhaps with Neptune, and sent on long, looping paths that bring them close to the Sun. When they approach the Sun, their ices vaporize, creating the glowing coma and the long, beautiful tails that we see from Earth. But out here in the Kuiper Belt, they are quiet and dark, their ices frozen solid, their surfaces unchanged for billions of years. They are the leftover building blocks of the solar system, material that never became part of a planet, preserved in the deep freeze of the outer reaches. The Kuiper Belt is vast, but it is not the end. Far beyond it, at distances that are almost impossible to visualize, lies a region called the Oort Cloud. The Oort Cloud is not a flat belt, but a huge spherical shell that is thought to surround the entire solar system. It is named after the Dutch astronomer Jan Oort, who proposed its existence in the year 1950. The Oort Cloud has never been directly observed. Its existence is inferred from the orbits of long-period comets, which come from all directions in the sky, not just the flat plane of the planets. These comets have orbits that suggest they originate from a distant reservoir of icy bodies, a shell that extends from perhaps 2,000 astronomical units to as far as 100,000 astronomical units from the Sun. To put that in perspective, 100,000 astronomical units is about 1.6 light-years. The nearest star to the Sun, Proxima Centauri, is about 4.2 light-years away. So the Oort Cloud, if it exists as theorized, may extend nearly halfway to the nearest star. It is the very edge of the Sun's gravitational hold, the boundary where the solar system fades into interstellar space. The objects in the Oort Cloud are thought to be icy bodies of various sizes, from small chunks to perhaps dwarf planet-sized worlds. They are so far from the Sun that they are only loosely bound by its gravity. A passing star or a disturbance in the galaxy can send one of these objects on a long, slow journey toward the inner solar system, where it will appear as a long-period comet, a visitor from the deep dark, appearing in our skies for a few weeks or months, before returning to the outer reaches, not to be seen again for thousands or millions of years. The Oort Cloud is the final repository of the solar system's original material, the outermost layer of the cocoon that surrounds our Sun and its planets. The distances involved here are so large that they can lull the mind into a kind of peaceful blankness. Light from the Sun takes hours to reach Pluto. It takes days to reach the inner edge of the Oort Cloud, and more than a year to reach its outer edge. The Sun, from the Oort Cloud, is just another star, indistinguishable from the thousands of other stars in the sky. The solar system, which seemed so vast when we began our journey at the Sun, now seems like a small, cozy neighborhood, a little cluster of worlds huddled close to their star. Out here, in the Oort Cloud, you would not feel the Sun's warmth at all. You would only know it by its faint light and by the gentle, almost imperceptible tug of its gravity, holding you in a slow, patient orbit that takes millions of years to complete. As we drift through this outermost region, we are approaching the end of our journey. There is one more section to come, a final, gentle drifting into the dark, where we will leave the solar system behind entirely and consider, for just a moment, the vastness of the galaxy beyond. But for now, let the quiet of the Kuiper Belt and the Oort Cloud hold you. Let the image of Pluto and Charon, that quiet double world, linger in your mind. Let the thought of countless icy bodies, unseen and unknown, drifting in their slow orbits, ease you closer to the stillness that waits at the end of the journey. The solar system is large, but you are safe within it, held by the same gravity that holds these distant worlds, drifting gently, gently toward the final quiet of the night. The image of Pluto and Charon lingers in the mind, that quiet double world, two small spheres of ice and rock turning slowly around each other in the deep dark. The countless icy bodies of the Kuiper Belt and the Oort Cloud drift in their slow orbits, unseen and mostly unknown, their paths taking thousands or even millions of years to complete. We have reached the edge of the solar system, the place where the Sun's influence fades into the background of the galaxy. And now, as we come to the final part of our journey, we are going to do something very simple. We are going to drift. Not toward any particular destination, not to visit any new world, but just outward, gently, into the quiet that lies beyond. The solar system, as large as it is only a tiny part of something much larger. Even the Oort Cloud, that vast, spherical shell that may extend a light year or more from the Sun, is just a small bubble within the galaxy. The Milky Way, our galaxy, contains somewhere between 100 billion and 400 billion stars. Each of those stars is a sun, and many of them likely have their own planets, their own solar systems, their own quiet worlds turning in the dark. The distances between stars are enormous. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. That means light, traveling at 300,000 kilometers every second, takes more than 4 years to make the journey from that star to ours. The distances between galaxies are larger still, millions of light years, stretches of space so vast that they are difficult to even speak about in a calm, measured way. And yet, here we are, a small part of it all, a tiny pocket of warmth and light in a universe that is mostly cold and dark and silent. There is a human-made object that has traveled farther from Earth than anything else we have ever built. It is called Voyager 1. It was launched in the year 1977, along with its twin Voyager 2, on a mission to explore the outer planets. After visiting Jupiter and Saturn, Voyager 1 was flung outward by Saturn's gravity, sent on a path that would carry it away from the plane of the planets and out into interstellar space. For decades it has been traveling, sending back faint radio signals to Earth, signals that take more and more time to reach us as it gets farther away. In the year 2012, Voyager 1 crossed a boundary called the heliopause. This is the place where the solar wind, the stream of charged particles that flows outward from the Sun, is no longer strong enough to push against the wind from other stars. Beyond the heliopause, Voyager 1 entered interstellar space, the region between the stars. It is still in the solar system, in the sense that the Sun's gravity still holds it, but it has left the protective bubble of the Sun's magnetic influence. It is drifting now, a small, silent craft, carrying a golden record with sounds and images from Earth, a message in a bottle cast into the cosmic ocean. It will continue to drift long after its power runs out, long after it stops transmitting, long after the Earth itself is gone. It will be a silent ambassador from a world that once was, carrying the memory of us into the dark. If Voyager 1 were aimed toward the nearest star, it would take about 70,000 years to get there. 70,000 years. That is longer than human civilization has existed. It is a span of time so long that it almost loses meaning. And yet, in the scale of the galaxy, 70,000 years is a short trip. The galaxy is about 100,000 light-years across. Light takes 100,000 years to cross from one side to the other. Our Sun, carrying the Earth and all the other planets with it, orbits the center of the galaxy once every 230 million years. The last time we were on this side of the galaxy, the dinosaurs had not yet evolved. The time before that, the continents were in different positions, the atmosphere was different, life itself was different. The galaxy turns, slowly, patiently, and we turn with it, a tiny speck in a vast, slow spiral of stars. This is the scale of things. It can feel overwhelming if you let it, but it can also feel deeply peaceful, because it means that whatever worries or stresses you might be carrying, they are very small in the grand scheme of things. The universe is vast, and it is mostly quiet, and it does not demand anything from you. It just is. And you are part of it, a tiny, living piece of it, here for a brief moment, looking out at the stars and wondering about them. That wondering is a beautiful thing. But right now, in this moment, you do not need to wonder. You just need to rest. Let us begin the slow journey back. We have drifted so far out, past the Oort Cloud, past the Kuiper Belt, past Neptune and Uranus, past Saturn and Jupiter, past the asteroid belt, past Mars and Earth and Venus and Mercury, all the way to the Sun, and then all the way back again to where we started. But we do not need to retrace every step. We can simply let the distance collapse, gently, like a folded piece of paper, bringing us back to the familiar. The solar system, which seemed so enormous when we were crossing it world by world, is really just a small neighborhood, a little cluster of planets around a fairly ordinary star. The star is one of billions in the galaxy. The galaxy is one of billions in the universe. And yet, here we are. Here you are, in your room, in your bed. The ceiling above you, the walls around you, the floor beneath you, the familiar sounds of your home, the creak of the building settling, the hum of a refrigerator somewhere in the distance, the soft sound of your own breathing. You have traveled a long way tonight. You have visited the Sun, that giant ball of hydrogen and helium, burning steadily for 4.5 billion years. You have drifted past Mercury, small and cratered, swinging wildly between extreme heat and extreme cold. You have paused at Venus, wrapped in its thick, acid clouds, spinning slowly backward, hotter than any other world. You have looked back at Earth, our home, blue and white and alive, with its single, constant moon slowly pulling away. You have wandered over the red deserts of Mars, with its ancient volcanoes and dry riverbeds, a world that may once have had water, may once have had life, but now keeps its secrets close. You have passed through the quiet, scattered stones of the asteroid belt, each one a tiny world, each one following its own path. You have marveled at Jupiter, the king of planets, with its swirling bands and its great red spot, and you have met its 4 large moons, Io with its volcanoes, Europa with its hidden ocean, Ganymede with its magnetic field, Callisto with its ancient, cratered face. You have admired Saturn, the ringed jewel, its icy particles catching the distant sunlight, its moon Titan wrapped in a thick haze, its moon Enceladus spraying water into space. You have rolled past Uranus, tilted on its side, a pale blue-green world of slow, patient seasons. You have stood at Neptune, deep blue and windswept, the last of the full planets, with its strange, captured moon Triton. And you have drifted out into the Kuiper Belt, past Pluto and Charon, past Eris and Makemake, and countless other icy bodies, out into the Oort Cloud, where the sun is just another star and the solar system fades into the interstellar dark. That is a long journey, and now you are back. The room is still, the darkness is quiet, your breathing is slow and steady, the earth is still turning, carrying you gently through the night, just as it has done every night of your life. The sun will rise in a few hours, and when it does, its light will take 8 minutes to cross the distance to your window. That light will have been traveling through the interior of the sun for tens of thousands of years before that, just to reach the surface and begin its journey to you. The warmth you will feel on your skin is ancient, patient, reliable. It has been coming to this planet for billions of years, and it will keep coming for billions more. For now, though, the sun is on the other side of the earth. You are on the night side, the cool, dark side, the side that faces out into space. Above you, if you could see through the roof and through the atmosphere, the stars are shining, the planets are moving in their orbits. The galaxy is turning, the universe is unfolding, slowly, quietly, at its own pace, and you are part of it, not separate from it, not an observer looking in from the outside, but a part of it, made of the same elements, governed by the same laws, held by the same gravity. You belong here. You belong to this universe, and it belongs to you. There is nothing you need to do now, no more facts to remember, no more distances to picture, no more worlds to visit. The journey is complete. You are here, in your bed, in the quiet dark, and the only thing left to do is let go. Let the thoughts drift away like the faint, icy bodies of the Oort Cloud, each one receding slowly into the distance. Let the sounds of the night become a soft, formless background. Let the weight of your body settle completely into the mattress, into the pillow, into the gentle pull of gravity that holds you safe and close. The solar system will still be there tomorrow night, and the night after that, and for all the nights of your life. The planets will keep turning, the sun will keep shining, the galaxy will keep spinning, and you, for this moment, can rest. You can close your eyes, if they are not closed already, and let the stillness take you. The universe is vast and quiet, and you are held within it, a small, warm point of consciousness, drifting gently into sleep. The journey is done, the dark is soft, the night is long and peaceful. Sleep well,